something is wrong. Not wrong in the way a calculation fails, not wrong in the way a prediction misses by a fraction, but wrong in the deepest possible sense. Wrong in the way that makes every assumption you have ever held about the nature of reality suddenly feel like it was built on something that was never really there. The universe, the vast, ancient, incomprehensibly large system that contains everything you have ever known, everything science has ever measured, everything philosophy has ever argued about, appears to be breaking its own rules. Not occasionally, not in edge cases that can be dismissed as rounding errors or incomplete data, but systematically, persistently, in ways that are growing harder to ignore with every new telescope we point at the sky, with every particle accelerator we push to higher energies, with every quantum experiment we run in the cold silence of a laboratory at 3 in the morning. The rules are breaking, and the most unsettling part is not that we cannot explain why. The most unsettling part is that we are beginning to suspect there may not be an explanation, because the rules themselves may never have been what we thought they were. And if exploring the cracks in reality is exactly why you're here, subscribe now to Beyond the Universe, because what comes next only gets stranger. You were taught to trust the universe. Maybe not explicitly, maybe not in those words, but the entire architecture of your education, your science, your technology, your civilization rests on a single foundational belief: that the universe follows rules, that those rules are consistent, that they apply everywhere at all times without exception, and that with enough intelligence and enough data, you can know them completely. This belief is so deeply embedded that it does not even feel like a belief. It feels like a fact. It feels like the ground beneath your feet. And for centuries it has served us well. We sent spacecraft to the outer edges of the solar system by calculating trajectories that were accurate to fractions of a millimeter across billions of kilometers. We split the atom by understanding forces so small they make a human hair look like a continent. We mapped the structure of DNA, engineered the genome, built machines that think. Every single one of those achievements depended on the assumption that the universe is lawful, that what happened yesterday will happen tomorrow under the same conditions, that the equations we write on a whiteboard in a university laboratory in one country will describe the same reality as the equations written in a laboratory on the other side of the world. That assumption has been the most productive idea in the history of human thought, and it may be wrong. To understand what is breaking, you first need to understand what was supposed to hold. Imagine the universe as a machine, an incomprehensibly vast, self-operating machine that has been running for approximately 13.8 billion years. This machine has rules. Physicists call them the laws of nature, but they are better described as the operating instructions of reality itself. These instructions tell matter how to behave in the presence of gravity. They tell light how fast to travel and in what direction. They describe how energy transforms from one form to another, how particles interact when they collide, how space bends in the presence of mass, how time flows relative to velocity. And crucially, these instructions are supposed to be the same everywhere. A hydrogen atom in a galaxy 12 billion light-years away is supposed to behave exactly the same as a hydrogen atom in your kitchen. The speed of light in the vacuum of space between distant galaxies is supposed to be the same as the speed of light we measure in our most precise laboratories. Gravity on the other side of the observable universe is supposed to follow the same inverse square law that Isaac Newton described while sitting under a tree in the 17th century. This is the bedrock. This is the thing that cannot move, except it is moving. The first cracks appeared quietly, the way the first cracks always do, in measurements that were slightly off, in data that did not quite fit the model, in numbers that were close but not close enough, in anomalies that researchers noted in the appendices of papers and then moved past because surely there was a systematic error somewhere. Surely the instruments needed recalibration. Surely a more careful analysis would bring everything back into alignment. The universe was not broken. The measurements were. That was the comfortable answer, and for a while it held. But then the anomalies did not go away. They sharpened. They deepened. They were confirmed by independent teams using completely different instruments, different methods, different assumptions. And the one that should have been the most straightforward, the one that seemed like it should have been the easiest thing in the world to measure correctly, the rate at which the universe is expanding, turned out to be one of the most destabilizing discoveries in the history of cosmology. You are probably familiar, at least in a general sense, with the idea that the universe is expanding. Ever since the early 20th century, astronomers have known that galaxies are moving away from each other, that the fabric of space itself is stretching, carrying everything embedded in it, apart from everything else. Edwin Hubble confirmed it. Einstein's equations predicted it. The Big Bang model explained it. and cosmologists developed a precise way of measuring how fast this expansion is happening, a number they call the Hubble constant, named after the man who first measured it. For decades, measuring the Hubble constant was considered a technical challenge, not a conceptual one. You measure it one way, from the early universe, using the faint afterglow of the Big Bang itself, the cosmic microwave background radiation, and you get a number. Then you measure it another way, from the local universe, using carefully calibrated distances to nearby galaxies, and you get a different number. These two numbers should be the same. They are describing the same universe. They are measuring the same rate of expansion, but they are not the same. They disagree by a margin that is far beyond what can be explained by measurement error, and the more precisely both measurements are made, the wider the disagreement becomes. This is not a rounding error. This is not a calibration issue. This is something that should not be possible, and it is happening anyway. Cosmologists have a name for this problem. They call it the Hubble tension, and the word tension is doing an enormous amount of work in that phrase. It sounds polite. It sounds manageable. It sounds like something that will eventually be resolved with better data or a smarter analysis. But what it actually represents is a fracture in the most fundamental model of cosmology ever constructed, a fracture that sits at the very heart of how we understand the origin, evolution, and ultimate fate of the universe. When you measure the expansion rate using the cosmic microwave background, using the Planck satellite's extraordinary precision measurements of the early universe, you get a value of approximately 67 kilometers per second per megaparsec. When you measure it using the cosmic distance ladder, using Cepheid variable stars and type Ia supernovae, and carefully calibrated local measurements, you get a value of approximately 73 kilometers per second per megaparsec. That difference of several kilometers per second per megaparsec might sound small. It is not. It means that either the early universe and the late universe are following different rules, or one of our measurement methods is catastrophically wrong, or our entire model of cosmological evolution, the standard model of cosmology, lambda CDM, the best description of the universe we have ever constructed, is missing something so fundamental that it has led us to a completely incorrect prediction about the most basic property of the universe. Every time a new measurement is made with greater precision, the tension is confirmed. It is not dissolving. It is hardening into something that looks less like a problem and more like a window into a reality that does not fit any framework we currently possess. You might think this is an isolated problem, a quirk of cosmological measurement that will eventually sort itself out. And you might hold that thought with some comfort, some reasonable skepticism about whether a disagreement between two measurement methods really constitutes a crisis. But the Hubble tension is not alone. It is not the only fracture. It is not even the most philosophically disturbing one. While cosmologists were wrestling with the expansion rate problem, particle physicists were having their own crisis, quieter and stranger, in the realm of the infinitely small. Specifically, they were watching particles behave in ways that their most successful theory, the standard model of particle physics, the most precisely tested scientific theory in history, said they should not. And perhaps the most unsettling example of this came from the muon, a particle you have probably never thought much about, which is exactly the kind of particle that turns out to matter enormously when it starts doing things it is not supposed to do. The muon is essentially a heavier version of the electron, a fundamental particle with electric charge, but roughly 200 times more massive. It does not last long. It decays in a fraction of a microsecond, but in that brief existence, it has a property called magnetic moment, a measure of how it responds to magnetic fields. The standard model of particle physics predicts this magnetic moment with extraordinary precision, taking into account all the virtual particles that briefly flicker in and out of existence around the muon, all the quantum corrections, all the interactions that contribute to its behavior. The prediction is so detailed, so refined, that it extends to 10 or 11 decimal places. It is one of the most precise predictions ever made in all of science. And when experimentalists at Fermilab in the United States measured the muon's magnetic moment with matching precision, the result did not match the prediction. Not by a lot, not by a number that shouts catastrophic failure, but by a small, statistically significant, stubbornly persistent difference that the physics community has come to call the muon anomalous magnetic moment problem, or G-2, after the technical parameter being measured. This result was not new. It had been seen before, at Brookhaven National Laboratory 2 decades earlier, when Fermilab confirmed and strengthened it using an independent experiment with better statistics. It became one of the most significant discrepancies between theory and experiment in the entire history of particle physics. The Standard Model, the theory that has successfully predicted every other particle physics measurement ever made, appears to be wrong about the muon. Something is interacting with that particle that the model says should not be there. Something is making it spin differently than the most successful physical theory ever constructed says it should, and nobody knows what it is. You might be starting to feel a particular kind of unease, not panic, not confusion exactly, but something more like the sensation of noticing that the floor you are standing on has a slight give to it that you had not noticed before. The rules are there. They still work mostly. They still make predictions, mostly correct ones, but there are these places, these specific, precise, carefully measured places, where reality deviates from the prediction in ways that cannot be dismissed. And you begin to wonder whether you are looking at exceptions or whether you are looking at the first visible cracks in a structure that is less solid than it appeared. To understand why this feels so significant, you need to appreciate just how extraordinary the Standard Model actually is. This is not a rough approximation. This is not a sketch. The Standard Model is the product of decades of the most sophisticated mathematical and experimental work in human history, refined by thousands of physicists across generations, tested in the most extreme conditions imaginable, in particle accelerators that smash protons together at energies that recreate conditions from the earliest fractions of a second after the Big Bang. It describes the electromagnetic force, the weak nuclear force, the strong nuclear force, and all the particles that carry and experience those forces. It predicted the existence of the Higgs boson before it was discovered, and when the Large Hadron Collider found it in 2012, it was exactly where the Standard Model said it would be. When reality starts diverging from a theory that has never once been wrong before, you do not shrug and move on. You sit with the discomfort and you start asking what it means. And then there is the matter of matter itself. The existence of the universe as a physical, solid, inhabitable place depends on a ratio, a balance between matter and antimatter that should not exist according to the laws of physics as we understand them. When energy converts into particles, which happened constantly in the first moments after the Big Bang and still happens in high-energy collisions today, it should produce equal amounts of matter and antimatter, one particle for every antiparticle, perfect symmetry, and then those particles and antiparticles should meet each other and annihilate, converting back into pure energy, leaving nothing behind. No atoms, no stars, no planets, no you. Just an ocean of photons stretching across an empty universe. That is what the rules predict. That is what should have happened. But something, some process, some asymmetry that has no satisfactory explanation in our current physics, tipped the balance ever so slightly in favor of matter. For every 10 billion antiparticles produced in the early universe, there were 10 billion and 1 matter particles. That extra particle, that 1 in 10 billion excess, is the reason everything exists. It is the reason you exist, and we have no idea why it happened. The violation of the symmetry between matter and antimatter, called CP violation in the technical language of physics, has been observed in certain particle interactions, but not nearly enough to explain the staggering imbalance that allowed the universe to contain anything at all. There is more matter in the universe than the laws of physics can account for. The rules say this should not be possible. The rules say the universe should be empty. And yet, here it is. Here you are, inside a universe that should not exist, observing rules that appear to be breaking, measuring constants that appear to be drifting, watching particles misbehave in ways that the most precise theories in human history cannot predict. And perhaps the strangest thing about all of this is that it has been building for decades, and yet the mainstream narrative of science still often presents itself as if the fundamentals are understood, as if we are filling in details, as if the architecture is sound and we are just doing interior decoration. But the architecture is not sound. The architecture has holes in it that are growing larger with every high-precision measurement, every unexpected cosmological observation, every quantum experiment that forces us to confront just how little we actually understand about why the universe behaves the way it does. To understand how deep these holes go, it helps to follow one of the most persistent and philosophically challenging anomalies in all of physics, the one that has been sitting in plain sight for over a century, the one at the heart of quantum mechanics itself, the one that describes what happens when a particle is not being watched. Quantum mechanics is the framework that describes the behavior of matter and energy at the smallest scales. It was developed in the early 20th century, and it is, by most measures, the most successful physical theory ever constructed. It has been tested more thoroughly than any other scientific framework, and it has never once been found wrong. Its predictions match experimental results to extraordinary precision, the kind of precision that makes the muon anomaly, small as it is, particularly jarring by contrast. But quantum mechanics has a problem. Not an experimental problem, not an anomaly in measurement, but a conceptual problem so fundamental that it has divided physicists for 100 years without resolution. The problem is this: quantum mechanics describes particles not as having definite properties, not as being in one specific place with one specific velocity, but as existing in a superposition of all possible states simultaneously, described by a mathematical object called a wave function. This wave function evolves smoothly and deterministically according to Schrödinger's equation. It spreads out, it interferes with itself, it describes not where a particle is, but the probability distribution of where it might be found if you look. And then you look, and something happens that Schrödinger's equation does not describe. The wave function collapses. The particle, which was in a superposition of states, is suddenly in one definite state. The spread-out cloud of probability snaps into a specific outcome, and nobody knows why. Nobody knows how. Nobody even agrees on whether this collapse is a physical process, a mathematical artifact, a consequence of consciousness interacting with matter, or something else entirely. This is called the measurement problem, and it is not a solved problem. It is not a footnote in a textbook. It is an open wound in the foundations of physics, a place where the rules demonstrably work in practice, but fail completely to explain themselves in principle. The universe, according to quantum mechanics, does not have definite properties until it is observed, which raises the question that nobody in 100 years of trying has been able to answer. What counts as an observation, and why does reality need to be watched in order to decide what it is? The implications of this question spiral outward in ways that feel increasingly disconnected from the comfortable solidity of everyday experience. You are sitting in a room right now. The chair beneath you feels real. The walls around you feel real. The air you are breathing, the light you are seeing, the sounds you are hearing, all of it feels stable, definite, located in space, occurring in time. But the atoms that make up every single one of those things, the chair, the walls, the air, the light, are not definite at the scale where quantum mechanics applies. They are described by wave functions. They exist in superpositions. The definiteness of your experience, the crisp, clear, solid reality you inhabit, emerges somehow from a substrate that is, at its most fundamental level, not crisp or clear or solid at all. It is probabilistic. It is fuzzy. It is described not by statements about what things are, but by statements about what things might be with what likelihood. How does the solid, definite world of your experience emerge from the indefinite, probabilistic world of quantum mechanics? This is the question. And the honest answer, the answer that every serious physicist who has thought carefully about it will give you, is that we do not know. We have interpretations, many worlds, which says the wave function never collapses, and instead every possible outcome occurs in a branching universe. Copenhagen, which says the collapse is a fundamental feature of measurement, and nothing more needs to be explained. Pilot wave theory, which says particles always have definite positions but are guided by a real wave that we cannot directly observe. Cubism, which says the wave function is not a description of reality, but a description of an observer's beliefs. These are not small technical differences in the same framework. They are fundamentally different claims about what reality is. And after a century, there is no consensus. The rules that quantum mechanics gives us work perfectly for making predictions. But those same rules, when you ask what they mean, when you ask what they say about the nature of reality, dissolve into a fog of competing interpretations that cannot be resolved by experiment, because every interpretation makes the same predictions. The equations work. But what the equations are describing, that remains, astonishingly, unknown. And while quantum mechanics was making the small strange, cosmology was making the large stranger still. You probably know that most of the universe is invisible. Not metaphorically invisible, not invisible because it is too far away or too dim to see, but literally invisible, made of something that does not interact with light at all, something that passes through ordinary matter like a ghost through a wall, something that reveals its presence only through its gravitational effects on the things around it. Dark matter. The name sounds ominous because the implications are ominous. Roughly 27% of the universe is made of this unknown substance. Another 68% is made of something even stranger, dark energy, the name given to whatever is causing the expansion of the universe to accelerate rather than slow down, whatever is pushing the cosmos apart with an energy that grows as space grows, defying every intuition about how forces should behave at cosmic scales. Together, Dark matter and dark energy account for 95% of the total energy content of the universe. The atoms, the particles, the stars, the planets, the galaxies, the nebulae, the electromagnetic radiation, the neutrinos, everything that the Standard Model describes, everything we have ever directly detected or measured or observed, constitutes roughly 5% of what exists. We have built the most precise theory of matter in history, and it describes 5% of the universe. The other 95% is labeled with words that mean we do not know what it is. We call it dark matter, dark energy, and we have been searching for dark matter particles for decades, in deep underground detectors shielded from cosmic rays, in colliders smashing protons together at the highest energies ever achieved, in astronomical observations, searching for the signatures of dark matter annihilation in the cores of galaxies, and we have found nothing. Every predicted signal, every promising candidate, every theoretical particle that should have revealed itself by now, has either not appeared or appeared only to vanish when looked at more carefully. The thing that makes up more than a quarter of the universe is completely invisible to every instrument we have built to find it. There is something almost hypnotic about the recursive quality of this problem. We know dark matter exists because of what it does, because of how it bends light, how it shapes the rotation curves of galaxies, how it influences the large-scale structure of the cosmic web. Galaxies rotate in ways that only make sense if there is enormous amounts of additional mass present that we cannot see. The outer stars of a spiral galaxy rotate at nearly the same speed as the inner stars, when gravity alone would demand that they slow down dramatically with distance from the center, just as the outer planets in our solar system orbit more slowly than the inner ones. The only explanation that fits the observations is a vast, diffuse halo of invisible mass surrounding every galaxy, extending far beyond its visible disk, providing the gravitational scaffolding that keeps the outer stars on their orbital paths. Every other explanation that has been proposed, modified theories of gravity, new physics that changes how gravity works at large distances, has failed to fully account for all the evidence. Dark matter is the simplest explanation that fits. But the particle that should be dark matter, the particle that theorists have been confidently predicting for decades, the weakly interacting massive particle, the WIMP, has not been found. The underground detectors have run for years and detected nothing. The colliders have produced no new physics. The satellites have seen no unambiguous annihilation signal. And every time the sensitivity of these experiments increases, every time we look harder, we find only the absence of what we expected to find. Not null, but quiet. Not nothing, but nothing where something was supposed to be. The silence from the dark sector has driven physicists to increasingly creative and increasingly desperate theoretical proposals. Perhaps dark matter is not made of WIMPs at all, but of axions, ultralight particles originally proposed to solve an entirely different problem in quantum chromodynamics, the theory of the strong force. Perhaps it is made of primordial black holes formed in the early universe before any stars existed, black holes so numerous and so massive that they constitute the missing matter without any new particle physics being required. Perhaps it is made of sterile neutrinos, particles that interact with ordinary matter only through gravity and nothing else. Perhaps it is a condensate, a quantum fluid that permeates the universe at galactic scales, behaving more like a wave than a particle. Each of these possibilities is being pursued, and each of them has its own predictions and its own experimental signatures. And so far, none of them have provided the decisive, undeniable detection that would settle the question. Meanwhile, every year that passes without detection of the most favored candidates is a year that constrains and shrinks the available parameter space, a year that rules out another range of possible masses and interaction strengths, a year that pushes the theory further toward territory where it is either unfalsifiable or simply wrong. The silence is data, and the data is telling us something we are not quite ready to hear. Dark energy is, if anything, even more philosophically troubling than dark matter. Dark matter, at least, is something, a substance, a material, something with mass that gravitates. Dark energy is a property of space itself, the name we give to the observation that empty space has energy, that the vacuum is not empty, that the very fabric of the universe between all the galaxies and all the matter contains something that is pushing outward, causing the expansion to accelerate rather than slow, and doing so with increasing effect as the universe grows larger and more space comes into existence. When Einstein first developed general relativity, he included a term in his equations called the cosmological constant, a term representing the energy density of empty space. He later called it his greatest blunder because it seemed to be an arbitrary addition with no physical motivation. Then, in 1998, two independent teams of astronomers studying Type Ia supernovae discovered that the expansion of the universe is not slowing down as it should under the influence of gravity, but accelerating. The cosmological constant was back, dark energy was real, and it needed to be explained. Quantum field theory, the framework that underpins both quantum mechanics and the Standard Model, predicts that the vacuum should have energy, virtual particles popping in and out of existence, quantum fluctuations in every field, a seething energetic soup of transient creation and annihilation, even in what we call empty space. This is not a theoretical speculation. The energy of the vacuum is real and measurable. The Casimir effect, a small attractive force between two uncharged metal plates placed extremely close together, is caused by quantum vacuum energy. It has been measured. It exists. But when you calculate how much energy the vacuum should have, using quantum field theory and the known particles and forces, you get a number. And when you compare that number to the observed value of dark energy, the thing that is causing the universe to accelerate, the discrepancy is so enormous that it has been described as the worst prediction in the history of physics. The calculated value is approximately 10 to the power of 120 times larger than the observed value. That is not a small error. That is an incomprehensible gulf between theory and reality. The most fundamental framework we have for understanding the quantum vacuum predicts that empty space should contain so much energy that the universe would have torn itself apart in its earliest moments, never forming stars or galaxies or anything at all. Clearly, that did not happen. But why the vacuum energy is so extraordinarily, precisely small compared to what theory predicts is one of the deepest unsolved problems in all of physics, and it has resisted every serious attempt at a solution for more than 2 decades. The cosmological constant problem is not just a technical puzzle. It is a signal that something is deeply, fundamentally wrong with how we are combining quantum mechanics and general relativity, the two greatest theories in physics, the two frameworks that together describe every physical phenomenon, from the smallest to the largest scale. Quantum mechanics governs the very small, general relativity governs the very large. Both are extraordinarily successful within their domains, and they are fundamentally incompatible with each other. Not slightly incompatible, not in need of minor adjustment. Mathematically, deeply, irreconcilably incompatible in their basic assumptions about the nature of space, time, and matter. General relativity is a theory of smooth, continuous, curved space-time. Quantum mechanics describes a world that is fundamentally discrete, probabilistic, and non-local. When you try to combine them, when you try to describe what happens at scales where both quantum effects and gravitational effects are significant, at the Planck scale, the unimaginably tiny scale of 10 to the power of negative 35 meters, the mathematics breaks down. It produces infinities. It becomes unpredictable. The equations stop working. And the place where the equations stop working is not some obscure corner of physics. It is the beginning of the universe. It is the interior of a black hole. It is everywhere that both theories should simultaneously apply, everywhere that reality operates at both quantum and gravitational scales, and neither framework extends far enough to describe what is actually happening. We have two theories, each perfect in its own domain, and no way to join them. The universe is described by two sets of rules that are not compatible with each other, and the universe itself, presumably, does not have this problem. It manages to be both quantum and gravitational at the same time, but we do not know how. You have probably heard of string theory. It is the most famous attempt to unify quantum mechanics and general relativity, to find a single framework that describes all forces and all particles and all interactions within one coherent mathematical structure. String theory replaces point-like particles with tiny, vibrating strings, and it requires additional dimensions of space beyond the 3 we experience, usually 10 or 11 dimensions in total. It is mathematically beautiful. It has produced stunning results in pure mathematics. And it has, after more than 50 years of intense development by some of the most brilliant theoretical physicists of our time, produced not a single testable prediction that has been confirmed by experiment. This is not a critique of the physicists who work on it. Many of them are aware of this situation and are deeply uncomfortable with it. String theory is currently neither confirmed nor falsified. It is not even clear that it is falsifiable in principle, because its predictions depend on the details of how the extra dimensions are compactified, and the number of possible configurations, the string theory landscape, is estimated to be 10 to the power of 500, an almost inconceivably large number of possible universes, each with different physical constants and different particle spectra. If string theory is correct, then our universe is one point in a landscape of possibilities so vast that the specific laws we observe may simply be accidents, the particular outcomes of an initial configuration that has no deeper explanation. The rules of physics in this picture would not be inevitable. They would be contingent. They would be the way things happen to be in our universe, not the way things must be in any universe. The inverse square law of gravity, the speed of light, the mass of the electron, the strength of the electromagnetic force, all of these could have been different, are different elsewhere in the landscape, and our universe has the values it has not, because those values are logically necessary, but because they are the values that allow complexity and life to emerge, and we are only here to observe them because we can only exist in a universe where they are what they are. This is the anthropic principle taken to its logical extreme, and it has the flavor of a theory that explains everything by explaining nothing, that replaces determinism with accident and necessity with coincidence. But the discomfort with string theory's landscape and the anthropic principle is not merely aesthetic. It touches something deeper, something about what it means for physics to be a science. Science works by making falsifiable predictions, statements about what will be observed that can be tested, and, if wrong, can refute the theory. A theory that can explain any possible set of observations by appealing to a sufficiently large landscape of possibilities is, in a precise sense, not a scientific theory at all. It is a framework that is consistent with everything, which means it is ruled out by nothing, which means it has no predictive power in the traditional sense, and yet it is the most developed framework we have for unifying the laws of physics. This is where we are. The deepest attempt at a theory of everything has left us in a place where the rules of physics might be arbitrary, where the constants of nature might be accidents, where the universe we inhabit is simply one draw from an impossibly large lottery of possible universes, and where any deeper explanation of why physics is the way it is may be permanently beyond reach. If this is correct, then the search for a final theory, a theory that explains not just how the universe works but why it works that way, is not a search that will eventually succeed. It is a search for something that does not exist. And while theoretical physicists were grappling with these foundational questions, experimental physicists were finding something else entirely, something that pushed the strangeness in a completely different direction. Quantum mechanics, as you have already encountered, is the framework that describes the very small, and one of its most celebrated and most experimentally well-confirmed features is entanglement, the correlation between quantum particles that Einstein famously dismissed as spooky action at a distance, the phenomenon by which two particles, once they have interacted and their quantum states have become correlated, continue to exhibit correlations in their measurements regardless of the distance between them. Measure the spin of one particle, and the spin of its entangled partner is instantaneously determined, no matter how far apart they are. This has been confirmed in experiments where the particles were separated by thousands of kilometers. It has been demonstrated between particles and satellites in orbit and detectors on the ground. The correlations exist, the entanglement is real, but it seems to violate something essential about how reality should work. The principle that what happens here cannot instantaneously affect what happens somewhere far away. The principle that information cannot travel faster than light. Einstein believed that entanglement was not really spooky, that there were hidden variables, predetermined properties that the particles carried with them from the moment of their interaction, properties that determined the outcome of any measurement in advance so that no mysterious instant communication was required. He was wrong. John Bell proved in 1964 that any theory with hidden variables of the local type that Einstein imagined would make different statistical predictions from quantum mechanics, and every experiment that has tested this, the Bell test experiments, repeatedly refined over decades, has confirmed quantum mechanics and ruled out local hidden variables. The correlations between entangled particles are not predetermined. They are genuinely random at the individual level and genuinely correlated at the statistical level in a way that cannot be explained by any locally realistic theory of the kind Einstein imagined. The universe is not locally real. The particles do not have their properties before they are measured, and yet they are correlated across arbitrary distances the moment they are. This is not a metaphor. This is what the experiments show, and nobody has a fully satisfying explanation for how it works. The mathematics of quantum mechanics predicts it perfectly, but the mechanism, the physical story of why two particles on opposite sides of the solar system would be instantaneously correlated without any signal passing between them, that story does not exist. The rules say this should happen, but the rules do not explain why the rules say this. Here is where the pattern starts to become visible. where the individual anomalies begin to cohere into something that looks less like a collection of unsolved problems and more like a signature of something systematic. You have the Hubble tension, the early universe and the late universe expanding at different rates, a fundamental inconsistency in the standard model of cosmology. You have the muon anomaly, the most precisely tested theory in physics making a prediction about a particle that does not match what is observed. You have the matter-antimatter asymmetry, the universe containing matter when the rules say it should contain nothing. You have dark matter, 27% of the universe's energy content made of something that interacts with nothing we can detect, despite decades of searching. You have dark energy, the cosmological constant, a number so precisely tuned to be small that the odds of it being accidental, by any reasonable calculation, are astronomical. You have the quantum measurement problem, the most successful theory in physics failing to explain what happens when reality is observed. You have the incompatibility of quantum mechanics and general relativity, the two frameworks that describe everything failing to coexist in the places where both should apply. You have Bell non-locality, the universe demonstrating correlations that cannot be explained by any theory in which things have definite properties before they are measured. None of these are isolated. None of these are in completely separate fields. They all share a common thread. In every case, the thing that is expected, the prediction of our best theory, the behavior demanded by the rules, is not what is observed, or if it is observed, it cannot be explained by the rules that predicted it. The pattern is not anomaly. The pattern is systematic deviation. You might find yourself asking, as many physicists ask themselves in the quiet hours of their working lives, whether these deviations are symptoms of the same underlying disease. Whether the Hubble tension and the muon anomaly and the cosmological constant problem and the measurement problem and Bell non-locality are all pointing at the same missing piece, the same fundamental gap in our understanding, the same place where the framework of physics silently fails and has been failing all along without our noticing. Some physicists think so. Some think we are approaching a moment of scientific revolution, comparable to the transition from Newtonian mechanics to relativity and quantum mechanics in the early 20th century, a moment when the accumulation of anomalies becomes too heavy for the existing framework to bear, when a new framework must emerge that explains not just the new phenomena, but also why the old framework worked as well as it did for as long as it did. The history of science has seen these revolutions before. Newtonian mechanics was the bedrock of physics for 200 years, tested and confirmed in every context available. And then, at the turn of the 20th century, two anomalies emerged that Newton's framework could not explain: the photoelectric effect and the perihelion precession of Mercury. And within a few decades, quantum mechanics and general relativity had replaced the old framework with something unimaginably stranger and more powerful. The old rules did not disappear. They remained valid in their domain, as approximations, as limiting cases of the deeper truth. But the deeper truth was nothing like what Newton had imagined, and the conceptual revolution required to reach it was so profound that it took an entire generation of physicists to absorb it. We may be living through the opening stages of the next revolution, and if we are, the anomalies we are watching accumulate now are not failures of measurement. They are the first legible sentences of a message from a reality that does not fit the framework we have built to contain it. But to understand the depth of what might be coming, you need to sit with what the current framework actually claims about the nature of reality, and why those claims are so difficult to surrender. The standard model of particle physics and the standard model of cosmology, lambda CDM, together constitute the most complete and most precise description of physical reality that has ever been achieved. They are not guesses. They are not rough sketches. They are mathematical structures of extraordinary precision and internal consistency, built from decades of the most careful experimental and theoretical work in human history, tested against the most demanding observations ever made, confirmed in context after context after context. The standard model predicted the existence of the W and Z bosons before they were found. It predicted the top quark. It predicted the Higgs boson. Lambda CDM correctly describes the large-scale structure of the universe, the distribution of galaxies, the pattern of fluctuations in the cosmic microwave background, the abundances of light elements produced in the first minutes after the Big Bang. These are not small achievements. These are extraordinary victories of human reason over the inscrutability of nature, and they are real. The question is not whether these theories are wrong in the sense of being useless or inaccurate within their domains of application. The question is whether they are complete, whether they are fundamental, whether they represent the deepest possible description of reality, or whether they are themselves approximations to something deeper that we have not yet found, approximations that work in most cases but fail in precisely the cases that should matter most. The history of science suggests the latter. Every framework that has ever been thought to be final has turned out to be approximate. Aristotelian physics described the world in terms of natural motions and essential properties, and was the dominant framework for nearly 2,000 years. Newtonian mechanics replaced it, and was so successful that it seemed unassailable, but it was replaced in turn by quantum mechanics and relativity, which are themselves incompatible with each other, and are therefore not the final answer. Each transition preserved what worked in the previous framework, but revealed that the previous framework's apparent solidity was the solidity of a very good approximation, not the solidity of fundamental truth. This pattern suggests that our current frameworks, the Standard Model, General Relativity, Lambda CDM, are approximations too. The question is, what are they approximating? What is the deeper structure that reduces to these frameworks in the regimes where they work, but differs from them in the regimes where they fail? And is that deeper structure even accessible to us? Is it something we can discover with more experiments, more powerful instruments, more clever mathematics? Or is it hidden behind a wall of complexity or a limit of observability that we cannot penetrate from inside the universe we inhabit? That last question has a name in philosophy of science, and it is one of the most uncomfortable questions you can ask. It is the question of the underdetermination of theory by evidence. The possibility that the data we can ever collect, no matter how much of it, no matter how precise, is insufficient to uniquely determine the correct theory of the underlying reality. For any finite set of observations, there are infinitely many possible theories that are consistent with those observations. Science eliminates most of them by the criterion of simplicity. You prefer the theory that explains the most with the fewest assumptions, the theory that is most elegant, most economical, most parsimonious. But simplicity is not a guarantee of truth. It is an aesthetic preference, a methodological rule of thumb that has historically served well, but has no logical necessity behind it. Reality is not obligated to be simple. Reality is not obligated to be describable by equations that fit on a page. Reality is not obligated to be comprehensible to beings whose cognitive apparatus evolved for the specific purpose of hunting animals and avoiding predators on the African savanna 100,000 years ago. The fact that we can do physics at all, that the mathematics we invent in our minds corresponds to the structures we find in nature, that the universe is, in Einstein's phrase, comprehensible, this is itself a deep mystery that has no explanation within physics. It is a precondition for doing physics at all, and it may or may not be a permanent feature of our situation. There may be aspects of reality that are simply not accessible to the kind of rational, mathematical investigation that has served us so well in the domains where it has worked. And if that thought makes you uncomfortable, if the idea that there might be fundamental limits to what physics can ever know feels like the ground shifting beneath you, then you are beginning to understand the particular quality of unease that lives at the frontier of theoretical physics right now. It is not the discomfort of a difficult problem that you believe is solvable. It is the deeper discomfort of not knowing whether the problem is solvable at all, not knowing whether the tools you have are the right tools, not knowing whether the framework you are working within is even pointed in the right direction. And this discomfort is not confined to the abstract reaches of string theory and quantum gravity. It has started appearing in places that feel much more concrete, much more immediate, in the behavior of constants that were supposed to be, by definition, constant. The constants of nature are the numbers that define how the universe works. The speed of light, the gravitational constant, Planck's constant, the fine structure constant, which determines the strength of the electromagnetic interaction and governs the behavior of atoms and molecules and chemistry and ultimately biology. These numbers are not derived from any deeper theory. They are measured. They are found to have specific values, and those values are then inserted into the equations as given. The question of why they have those particular values rather than some other values is one of the deepest unanswered questions in physics. But there is a prior question that is just as important and considerably more unsettling. Are they actually constant? Are these numbers truly fixed, truly the same everywhere and at all times? Or have they been changing over the history of the universe, slowly drifting, evolving, different in the early universe from what they are today, different in distant regions of space from what they are nearby? For most of the history of science, the constancy of the constants was not something that needed to be demonstrated. It was assumed, it was baked into the framework. If the constants could vary, if the fine structure constant was different 10 billion years ago, then the atoms of that era would have had different energy levels, different emission spectra, different chemistry, and we can actually test this because the light from very distant quasars, traveling for billions of years to reach our telescopes, carries the fingerprints of the atoms it passed through in the early universe. If the fine structure constant was different then, the spectral lines in that ancient light would be shifted by a characteristic amount that we can calculate and look for. In 1999, a team of astronomers led by John Webb at the University of New South Wales announced that they had found exactly this signal. Analyzing the absorption spectra of quasars using the Keck telescope in Hawaii, they reported evidence that the fine structure constant was slightly smaller in the early universe, by about 6 parts per million, than it is today. This was, if confirmed, one of the most extraordinary discoveries ever made. Evidence that one of the fundamental constants of nature is not constant, that the rules of physics have been changing over cosmic time. The result was received with considerable skepticism. It was a difficult measurement, subject to many potential systematic errors, and extraordinary claims require extraordinary evidence. Subsequent studies produced contradictory results. Some confirmed the variation, some found no variation, some found variation in the opposite direction in different regions of the sky, which raised the even more exotic possibility that the fine structure constant varies not just in time, but in space, that it has a preferred direction across the cosmos, as if the universe has a handedness, an orientation, an anisotropy that violates one of the most fundamental assumptions of cosmology, that the universe looks the same in all directions on large scales. This assumption is called the cosmological principle, and it is not merely a convenience. It is the foundation on which all of modern cosmology rests. If the universe has a preferred direction, if it is not isotropic, then lambda CDM, built on the assumption of isotropy, is not just incomplete, it is systematically wrong in a way that affects every conclusion it has ever drawn. The evidence for violations of the cosmological principle has been growing quietly for years, accumulating across multiple independent observations in ways that are increasingly difficult to dismiss. There is the hemisphere asymmetry in the cosmic microwave background, the faint but statistically significant difference between the temperature fluctuation pattern on one side of the sky and the other, a difference that should not exist if the universe has no preferred direction. There is the cold spot, a region of the cosmic microwave background that is anomalously cold, anomalously large, and anomalously structured in ways that the standard model of inflation and the standard cosmological model struggle to explain. There is the alignment of certain large-scale structures in the universe, the orientations of quasar spin axes, the alignments of galaxy clusters that appear correlated across distances so vast that, under standard cosmology, they should be completely uncorrelated, separated by more space than any causal influence could have crossed since the Big Bang. And there is the dipole anisotropy in the distribution of distant radio sources and quasars, which points in a direction slightly different from the direction expected based on our motion relative to the cosmic microwave background. A discrepancy that, if real, suggests the universe's large-scale structure is not what the standard model predicts. Each of these observations, taken alone, might be a statistical fluke. Taken together, they suggest that the cosmos may not be as smooth, as uniform, as isotropically distributed as the cosmological principle demands. And if the cosmological principle fails, if the universe has structure at scales we thought were featureless, the implications cascade through every conclusion cosmology has drawn from assuming otherwise. There is a particular quality to the experience of watching the cosmological principle, one of the most foundational assumptions in all of science, come under systematic pressure. It is not the sharp shock of discovering a single anomaly. It is more like the slow cumulative realization that the map you have been navigating by has been slightly wrong in ways that individually seemed trivial, but that, added together, have led you somewhere you do not recognize. The cosmological principle is not just a mathematical convenience, it is an expression of a philosophical commitment, the commitment to the idea that our location in the universe is not special, that there is no center, no preferred direction, no cosmic address that matters in the description of physical law. This is the Copernican principle extended to its maximum scope. Copernicus told us the Earth is not the center of the solar system. Bruno and later cosmologists extended this. The sun is not special. Our galaxy is not special. Our place in the universe is not special. The universe is the same everywhere, at all scales. If this is wrong, If the universe does have structure, directionality, and isotropy, then the most fundamental principle of modern scientific humility is under threat. We may be somewhere specific. The rules may depend on where you are. This idea, that the rules of physics might depend on location, is so corrosive to the standard framework that it deserves to be held steady for a moment while you absorb its implications. If the fine structure constant is different in different regions of space, then the physics of atoms is different in those regions. The energy levels of hydrogen, the chemistry of molecules, the behavior of materials, the possibility of biology, all of these would be different in regions where the constants are different. The laws of nature would not be universal. They would be local, approximate, varying continuously across the cosmos in ways we cannot observe from our particular vantage point. The equations we have derived from experiments conducted here, in this tiny corner of the observable universe over this tiny slice of cosmic time, would be valid only in this neighborhood, only in this era. They would be no more universal than the weather patterns of a particular city on a particular day, locally describable, locally predictable, but not generalizable to the whole. If you take this possibility seriously, and there are serious physicists who do, then the entire project of finding a final theory of everything, a set of equations that describes all of physics everywhere and at all times, may be misconceived. Not because we are too stupid to find it, but because it does not exist. Because the universe does not have global rules. Because it has only local ones. And yet, even as these ideas push at the edges of what science can confidently claim, there are experimental results closer to home, results from laboratories and particle accelerators that are pushing in the same direction with a different kind of force. The Large Hadron Collider at CERN is the most powerful particle accelerator ever built. It smashes protons together at energies of 14 trillion electron volts, creating conditions that replicate the first fractions of a second after the Big Bang, and allowing physicists to probe the structure of matter at the smallest scales ever investigated. The discovery of the Higgs boson in 2012 was its greatest triumph, the confirmation of the last missing piece of the Standard Model. But since then, something unusual has been happening. The LHC keeps running. It keeps smashing. It keeps producing data in quantities that would have been incomprehensible to earlier generations of physicists. And it keeps not finding anything new, not finding any of the particles predicted by supersymmetry, the theoretical framework that would provide dark matter candidates, solve the hierarchy problem, and point toward a deeper unification of the forces, not finding extra dimensions, not finding any of the new physics that theorists had confidently expected would emerge once energies reached the levels the LHC was designed to probe. The machine is working perfectly. The Standard Model predictions are confirmed to extraordinary precision, and there is nothing else. The silence is as loud in its own way as the muon anomaly. Different kind of silence. Not the silence of a signal that should be there and is not quite there, but the silence of an entire landscape of predicted phenomena that should have appeared by now and have not appeared at all. Theorists had expected supersymmetry to show up at LHC energies. It has not. They had expected some sign of compositeness in the Higgs boson, some hint of structure at higher energies. There is none. The Standard Model sits there, perfect and complete and utterly baffling in its completeness. Because if it is complete, if there is genuinely nothing new at the scales the LHC can probe, then it means the next layer of physical structure, if it exists, is at energies so far beyond the LHC's reach that we have no realistic prospect of accessing it in any experiment we can currently imagine building. This is the nightmare scenario for experimental particle physics, and it has a name: the desert. The desert is the hypothetical possibility that between the energies accessible to current experiments and the Planck energy, the energy scale at which quantum gravity becomes important, some 15 orders of magnitude higher than the LHC, there is nothing. No new particles, no new forces, no new phenomena, just the Standard Model, extending unchanged across an enormous range of energies, until you reach the point where quantum gravity kicks in and everything breaks down. If the desert is real, then particle physics cannot proceed by its traditional method of building larger accelerators to reach higher energies. The energies required to access Planck scale physics are so extreme that no physically conceivable accelerator built on Earth, or even in the solar system, could reach them. The desert would mean that the next layer of physical law, the layer that unifies quantum mechanics and gravity, the layer that explains dark matter and dark energy, and the matter-antimatter asymmetry, is permanently beyond experimental reach. We would be trapped at the current level of understanding indefinitely, able to describe but never to explain, able to confirm the Standard Model, but unable to transcend it. This is not a guaranteed outcome. It is not even the most likely outcome, according to some theoretical arguments. But after more than a decade of the LHC finding nothing new, the possibility of the desert has moved from theoretical nightmare to serious consideration. You might find yourself returning to a question that has been circling throughout all of this, growing more insistent with each new anomaly, each new inexplicable observation, each new silence where a signal was expected. What if the problem is not that we are missing specific pieces of the puzzle, but that the puzzle itself, the framework within which we are trying to fit the pieces, is fundamentally misconceived? What if physics has been asking the right questions with the wrong language, building the right equations but misinterpreting what they mean, finding the right mathematical structures but placing them in the wrong conceptual context? This is not an unprecedented situation in the history of science. There have been periods when progress stalled not because the data was insufficient, but because the conceptual framework within which the data was being interpreted was wrong in a way that could not be fixed incrementally. The transition from caloric theory to thermodynamics did not happen by adding a better description of caloric. It happened by abandoning the concept of caloric entirely and replacing it with something completely different. The transition from Newtonian absolute space and time to Einsteinian space-time did not happen by refining the notion of absolute time. It happened by recognizing that absolute time was not a feature of reality at all. The next conceptual revolution in physics may similarly require abandoning something that currently seems as fundamental and indispensable as absolute time seemed in 1900. What might that something be? Several candidates have been proposed, and each of them represents a conceptual sacrifice so radical that it is difficult to contemplate without a sense of intellectual vertigo. One possibility is that spacetime itself, the four-dimensional continuum of three spatial dimensions and one time dimension that has been the background of all physical description since Einstein, is not fundamental, that it is emergent, arising from something deeper, something that does not look like space or time at all. This idea has been gaining traction from multiple directions simultaneously. In the theory of loop quantum gravity, one of the main competitors to string theory as an approach to quantum gravity, the smooth, continuous fabric of spacetime breaks down at the Planck scale into a discrete network of nodes and links, a spin foam, a kind of quantum geometry from which the smooth spacetime of general relativity emerges only at larger scales, the way the smooth surface of a liquid emerges from the discrete arrangement of individual molecules. In holographic theories inspired by string theory, spacetime itself is a projection, a lower dimensional reality arising from a higher dimensional quantum system living on the boundary of that space, the way a hologram produces a three-dimensional image from a two-dimensional surface. In these frameworks, what we call space, the three-dimensional volume in which everything exists, the medium through which forces propagate, the stage on which all of physics unfolds, is not the most fundamental level of description. It is a convenient approximation, a macroscopic average of something more primordial that does not have the geometric character of space at all. If space-time is emergent, then many of the deepest puzzles in physics take on a different character. The incompatibility of quantum mechanics and general relativity would be explained. They are incompatible because general relativity is a description of emergent space-time, and quantum mechanics is a description of the more fundamental layer from which space-time emerges, and of course a theory of the emergent layer and a theory of the fundamental layer will look incompatible when you try to apply both in the same regime. The cosmological constant problem might be dissolved. The enormous vacuum energy predicted by quantum field theory does not gravitate in the way we think, because the relationship between the quantum vacuum and space-time geometry is not what we assumed. The measurement problem in quantum mechanics might find a resolution in the structure of the underlying reality from which classical space-time emerges. None of this is proven. These are speculations, educated and mathematically sophisticated speculations, but speculations nonetheless. But they share a common theme, the possibility that what we take to be fundamental is not fundamental, that the rules we have discovered are rules of the emergent world, not of the underlying one, and that the underlying one follows completely different principles that have not yet been identified. There is another possibility that is harder to discuss without immediately sounding like you have left the realm of serious science, but which has been taken with increasing seriousness by an increasing number of physicists, cosmologists, and philosophers of physics. The possibility that the universe is not a physical object at all in the traditional sense, not a collection of matter and energy arranged in space and time and evolving according to fixed laws, but something more like a mathematical structure or an information processing system, or, in the most radical version, a simulation. The simulation hypothesis is often presented in popular culture as a kind of science fiction conceit, a thought experiment borrowed from the Matrix, interesting but ultimately untestable and therefore not really a scientific proposition. But when taken seriously, when examined carefully from the perspective of what quantum mechanics actually tells us about the nature of reality, it becomes harder to dismiss than it first appears. Consider what quantum mechanics says. Particles do not have definite properties before they are measured. The universe, at its most fundamental level, does not consist of things with properties. It consists of probability amplitudes, complex numbers whose squared magnitudes give probabilities for outcomes of measurements. The physical world, the world of definite particles and definite positions and definite momenta, exists only at the level of measurement outcomes, only at the level of information recorded by observers. The mathematics of quantum mechanics does not describe a world of things. It describes a world of information, of probabilities, of relationships between observational outcomes, and this has led some physicists, including serious and respected ones, to the conclusion that information, not matter, is the fundamental currency of reality. John Wheeler, one of the great physicists of the 20th century, the man who coined the term black hole, spent the latter part of his career developing a philosophy he summarized in 3 words: it from bit. The idea that the physical world, all the it of matter and energy and space-time, emerges from bit, from information, from the answers to yes or no questions posed by acts of measurement and observation. This is not a simple idea. It does not mean that the universe is a computer simulation in the crude sense of being run on some external hardware. It means something deeper and stranger, that the most fundamental description of reality is informational, that existence itself is constituted by information rather than containing it. This resonates with developments in theoretical physics that Wheeler could not have fully anticipated. The holographic principle, which emerged from the study of black hole thermodynamics and string theory, states that all the information needed to describe a 3-dimensional region of space can be encoded on the 2-dimensional boundary of that region, like a hologram, but in a much deeper, more fundamental sense. Black holes, it turns out, have entropy proportional to the area of their event horizon, not their volume. This is profoundly strange. It suggests that the maximum amount of information that can be packed into a region of space is determined by its surface area, not its volume, as if the 3rd dimension of space is in some sense redundant, as if what looks like a 3-dimensional world is actually a 2-dimensional information structure that generates the experience of depth. If information is fundamental, if the universe at its deepest level is a structure of information rather than of matter, then the rules of physics, the laws that govern how matter and energy behave, are not descriptions of a physical substrate. They are descriptions of patterns in information, regularities in a data structure, and the violations of those rules that we have been cataloging throughout this exploration take on a different meaning. They are not breakdowns of physical law. They are anomalies in the data, inconsistencies in the information structure, glitches in the pattern that are revealing the seams of the underlying system. The word glitch is loaded. It carries connotations that are difficult to take seriously in a scientific context. Associations with software errors, with simulated worlds, with the science fiction imagery of reality flickering at the edges. But the concept it points to, the idea that what looks like a violation of physical law might be a sign of the structure of the system that generates what we call physical law, is not inherently unscientific. It is, in fact, compatible with several rigorous theoretical frameworks that are being actively developed by serious physicists. The question of whether we live in a simulation, in the specific sense of whether our observable universe is a computation being run on some substrate external to itself, is genuinely difficult to answer from inside the system. By design, any sufficiently advanced simulation would be indistinguishable from a base-level reality to the observers within it, assuming the simulation was running accurately. But a simulation running at finite computational resources would have signatures, discreteness at small scales, computational shortcuts at large scales, anomalies at the boundaries of the simulated region, violations of conservation laws in extreme conditions. Some of these signatures, interestingly, are things we have actually observed. The discrete structure of space, suggested by loop quantum gravity, the tension between quantum mechanics and general relativity at Planck scales, the anomalies in the cosmic microwave background at the largest scales of the observable universe, the measurement problem, which looks, from certain angles, like the problem of rendering. Quantum mechanics might be computing only what is being observed, updating only the parts of the universe that are being measured, which would be an extremely efficient way to run a universe simulation on limited computational resources. You are probably feeling something complicated right now. A mixture of fascination and resistance, the sense that you are being pulled toward ideas that seem too strange, too speculative, too disconnected from the solid empirical ground of real physics. And that resistance is healthy. It is the resistance of a mind that has been trained to distinguish between what is known and what is guessed, between what is demonstrated and what is imagined. But the resistance should not be total, because the ideas that seem strangest have a way of becoming the most important. In 1900, the idea that space and time were not absolute, that they were relative, that they bent in the presence of mass, that they could be woven together into a four-dimensional fabric, these ideas would have sounded insane to anyone trained in the physics of Newton and Maxwell. In 1920, the idea that a particle could be in two places at once, that it could be both a wave and a particle, that its properties did not exist before they were measured, these ideas did sound insane, even to many of the physicists who developed them. Max Planck said that science advances one funeral at a time. New ideas do not win by persuading their opponents. They win by outlasting them. And the ideas that seem to be winning right now, slowly, reluctantly, in the face of accumulating anomalies and failing predictions, are the ones that say the framework is wrong at a deep level, that the rules are not what we thought they were, and that the universe does not care about our intuitions about how it should behave. One of the most profound and most neglected of these ideas concerns the nature of time itself. Of all the things that feel most certain, most immediate, most undeniable in your experience, time is perhaps the most fundamental. You experience the present moment. You remember the past. You anticipate the future. The flow of time from past to present to future is so deeply embedded in every aspect of your conscious experience that questioning it feels like questioning consciousness itself. And yet physics, both classical and quantum, has almost nothing to say about the direction of time in the fundamental sense, and what it does say is deeply troubling. The laws of classical physics, Newton's mechanics, Maxwell's electrodynamics, even Einstein's general relativity, are time-symmetric. They work equally well in both directions of time. If you filmed a planetary system orbiting a star and ran the film backward, you would not be able to tell from the physics alone that it was running backward. The equations do not distinguish between past and future. The universe of classical physics has no arrow of time. The second law of thermodynamics introduces an arrow. Entropy, the measure of disorder in a system, tends to increase over time, and this gives a direction to time, a way to tell past from future. But the second law is statistical, not fundamental. It is not a law in the same sense as Newton's laws. It is a statement about the overwhelming probability that a macroscopic system of many particles will evolve toward states of higher disorder, because there are vastly more disordered states than ordered ones. But probabilistic overwhelm is not the same as physical necessity. In a universe of infinite time, even the most extraordinary decreases in entropy would eventually happen spontaneously. The arrow of time, in the standard framework, is a consequence of the particular low entropy initial condition of the Big Bang, not of any fundamental asymmetry in the laws of physics. The universe started in an extraordinarily ordered low entropy state, and it has been evolving toward higher entropy ever since. But why it started in that state, why the Big Bang was the beginning of a trajectory from maximum order toward maximum disorder, is not explained by any current theory. It is another initial condition that is simply assumed. In quantum mechanics, the situation with time is even stranger. The Schrödinger equation, which governs the evolution of quantum states, is also time-symmetric. It does not have a built-in direction of time. The collapse of the wave function, however, the moment when a quantum superposition becomes a definite classical outcome, appears to be irreversible. Once the wave function collapses, you cannot unmeasure a particle. The information about its previous superposition is lost, scattered into the environment, impossible to recover. This irreversibility might be where the arrow of time comes from at the quantum level, but it also circles back to the measurement problem, because the collapse of the wave function is the thing that quantum mechanics describes but cannot explain. The arrow of time, the most fundamental feature of experienced reality, depends on a process, wave function collapse, that the theory does not account for. And some of the interpretations of quantum mechanics that try to get rid of collapse, particularly the many worlds interpretation, are perfectly time-symmetric, which means they eliminate the arrow of time entirely at the fundamental level and must explain your experience of a single, definite forward-moving time as an emergent feature of a vastly larger structure with no intrinsic direction at all. The thing that feels most certain to you, the flow of time, the reality of the present moment, the fact that the past is fixed and the future is open, is, in the physics of quantum mechanics, either unexplained or explained away as an illusion arising from your position as an observer within a timeless branching static mathematical structure. And there is a physicist, Julian Barbour, who has taken this seriously enough to develop a complete alternative framework for physics in which time does not exist at all. Not time as a fundamental feature of reality, not time as an arena in which events occur. Barbour's universe is a configuration space, an abstract mathematical space of all possible arrangements of matter, called Platonia, in which every moment exists as a static point, a frozen configuration, with no before or after, no evolution, no flow. What we experience as the flow of time is, in Barbour's framework, an illusion arising from the way memories are encoded in the structure of each configuration. Each frozen moment contains, within the arrangement of matter it describes, the record of a past, the sense of having arrived here from somewhere else. You are not moving through time. You are a static configuration that contains, encoded in the structure of your brain and your environment, the experience of having moved through time. This framework is not mainstream. It is not accepted by most physicists, but it is mathematically coherent, it is internally consistent, and it points to something that mainstream physics cannot fully explain: why time feels the way it does when the fundamental equations are time-symmetric. The discomfort it produces is not the discomfort of a bad idea. It is the discomfort of an idea that takes seriously what the equations say at the cost of what your senses tell you. And that tension, between the mathematics and the experience, between the formal description and the felt reality, is at the heart of everything that makes the foundations of physics so deeply unsettling right now. Perhaps the most quietly devastating of the foundational issues in physics is the one that is rarely discussed in popular science because it does not have a dramatic discovery attached to it, no sudden experimental result that forced it into consciousness, but has been sitting in the background of everything for over half a century, accepted by most physicists as a feature rather than a problem, even as a small number of thinkers have recognized it as perhaps the deepest problem of all. It is the problem of fine-tuning, and it is this: the constants of nature, the numbers that define the strength of each force, the mass of each particle, the energy of the vacuum, are not just specific numbers. They are specific numbers that, if they were even slightly different, would result in a universe incapable of containing any complexity whatsoever. A universe in which the strong nuclear force was a few percent weaker would be a universe in which atomic nuclei could not hold together, in which there would be no atoms beyond hydrogen, no chemistry, no stars, no planets, no life. A universe in which the cosmological constant was a few orders of magnitude larger would be a universe in which space expanded so rapidly that matter never had time to clump into galaxies. A universe in which the electromagnetic force was slightly stronger or weaker would be a universe in which chemistry did not work in the ways that allow complex molecules to form and replicate. The values of the constants appear to be tuned, calibrated, set to specific numbers in a narrow range that allows the universe to be complex, interesting, and inhabited. This is the fine-tuning problem, and it has three possible resolutions. The constants were chosen by design, the constants were set randomly, and we are simply in one of the lucky configurations, the anthropic principle, or the constants are determined by some deeper physical principle that we have not yet discovered, a principle that makes them necessary rather than contingent. All three options have profound problems. The first is not a scientific explanation. The second is an explanation only in the context of a multiverse, a collection of universes with different constants, of which ours is one of the inhabitable ones. But the multiverse is not directly observable and may never be, and it raises its own questions about why the multiverse has the properties it has. The third has the problem of not existing yet, of being a promissory note on a theory that nobody has written. The fine-tuning sits there, demanding an explanation, and every explanation that has been proposed either requires an entity outside the universe, or a collection of universes outside our observation, or a deeper physics that nobody has found. At this point in the journey, you may have noticed something about the structure of what you have been encountering. Every time you pull on a thread, every time you follow an anomaly to its root, Every time you ask why the rule is violated, or why the constant has its value, or why the measurement produces a result different from the prediction, you find not a solid bottom but another layer, another question, another regime where the current framework fails or admits its own incompleteness. The Standard Model is incomplete at the boundaries where it meets general relativity. General relativity is incomplete inside black holes and at the Big Bang. Quantum mechanics is complete in its predictions but incomplete in its interpretation. Lambda CDM is complete in its description of the universe's evolution, but incomplete in its description of 95% of what it is evolving. String theory is potentially complete as a mathematical framework, but incomplete in its connection to observable physics. Loop quantum gravity is mathematically well defined, but has not reproduced general relativity in the appropriate limit to everyone's satisfaction. Every framework has a beyond, a regime or a question where it runs out of road, and the beyonds of these frameworks are not empty. They are full of the most important questions we can ask about the nature of reality. The hierarchy problem asks why gravity is so much weaker than the other forces, why the mass of the Higgs boson is not driven to the Planck mass by quantum corrections. The information paradox asks what happens to the information encoded in matter that falls into a black hole, whether it is preserved or destroyed, and what the answer means for the fundamental laws of physics. The initial conditions problem asks why the universe began in the extraordinarily low entropy state that gave rise to the arrow of time. The measurement problem asks how definite classical reality emerges from indefinite quantum superposition. The origin problem asks what preceded the Big Bang, or whether the concept of precedence even applies to the boundary of time itself. These are not peripheral questions. They are not puzzles at the edge of an otherwise complete picture. They are the central questions, the ones that the picture was supposed to answer and has not, the ones that every framework either ignores by assumption or explicitly marks as outside its scope, and the fact that they remain unanswered, not just technically but conceptually, not just lacking solutions but lacking even agreed frameworks for what a solution would look like. This is the situation that faces physics in the early 21st century, not a triumphant march toward a final theory, a deepening labyrinth, beautifully mapped in the regions already explored, opening into new passages at every apparent dead end, with no clear indication of whether the center of the labyrinth is a discovery waiting to be made, or a void that was never there to be found. Consider for a moment the information paradox, because it captures better than almost any other problem the quality of breakdown that characterizes the current moment in theoretical physics. The information paradox was first clearly articulated by Stephen Hawking in 1974, following his extraordinary discovery that black holes are not completely black. They emit radiation, what we now call Hawking radiation, a thermal glow produced by quantum effects near the event horizon, the boundary beyond which nothing can escape the gravitational pull of the black hole. This radiation slowly carries away the mass of the black hole until, over an almost incomprehensibly long time, the black hole evaporates completely, leaving nothing behind except the radiation it emitted. Now, the radiation is thermal. It is random, characterized only by a temperature that depends on the mass of the black hole. It carries no information about what fell into the black hole in the first place. If a book fell in, or a star, or a specific configuration of particles in a specific quantum state, the radiation that emerges carries no record of what was there. The specific quantum information, the particular arrangement of quantum states that characterize the infalling matter, appears to be destroyed. This is a problem because the fundamental laws of quantum mechanics are unitary, which means they preserve information. The evolution of a quantum state is always reversible. You can never truly destroy information in quantum mechanics. Every process that scrambles or hides information does so in a way that, in principle, allows the original state to be reconstructed from the final state, given complete knowledge. Hawking's calculation says that black hole evaporation destroys information. Quantum mechanics says this is impossible. Both black hole physics and quantum mechanics cannot be right. One of them must give. For nearly 50 years, this paradox has resisted resolution. Hawking himself spent decades defending the information destruction thesis before eventually conceding in 2004 that information probably is preserved. But the mechanism by which it is preserved, how the information that fell into the black hole is encoded in the outgoing Hawking radiation in a way that is in principle recoverable, is not understood. Recent work by Ahmed Almhairi, Netta Engelhardt, and others using the island formula and quantum extremal surfaces has made progress on understanding the information content of the radiation, but the full resolution remains elusive and the conceptual implications remain profound. A black hole is a region where the rules of quantum mechanics and the rules of general relativity come into direct conflict, and neither wins cleanly. The black hole information paradox has a sibling that is, if anything, even more viscerally disturbing. The firewall paradox, proposed in 2012 by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, usually referred to as AMPS, after the author's initials. Their argument went like this: quantum mechanics requires that the information in infalling matter be preserved in the Hawking radiation, which requires that the early and late parts of the Hawking radiation be quantum entangled with each other, which uses up the entanglement budget of the outgoing radiation. But general relativity requires that the infalling observer crossing the event horizon experience nothing special. The equivalence principle, one of the foundations of general relativity, demands that the event horizon be locally indistinguishable from empty space to a freely falling observer. The problem is that the mathematics of quantum entanglement says these two requirements cannot both be satisfied simultaneously. If the early Hawking radiation is entangled with the late Hawking radiation to preserve information, it cannot also be maximally entangled with the infalling matter to make the horizon look smooth and empty. Something at the horizon must give. And AMPS argued that what gives is the smoothness, that the event horizon is not the invisible, gentle boundary that general relativity predicts, but a wall of high-energy radiation, a firewall, that incinerate anything falling through it. But if this is right, then the equivalence principle is violated at the horizon, and one of the most fundamental tenets of general relativity fails precisely at the place where you need it to hold. The firewall paradox does not have an agreed resolution. It has been argued about intensely since its publication. It has generated an enormous amount of theoretical work. It has given rise to astonishing proposals, including the idea that the interior of a black hole is connected to the exterior Hawking radiation by a network of wormholes, that the entanglement between particles is literally a geometrical connection in spacetime, a proposal encapsulated in the formula ER equals EPR, where ER refers to the Einstein-Rosen bridge, a wormhole, and EPR refers to the Einstein-Podolsky-Rosen entangled pair. This is a beautiful and audacious idea, that quantum entanglement between two particles is physically equivalent to a wormhole connecting them, that the geometry of spacetime and the entanglement structure of quantum mechanics are two descriptions of the same underlying reality. It would mean that spacetime connectivity, the fact that different regions of space are near or far from each other, is a consequence of quantum entanglement, not the other way around. That entanglement weaves spacetime together, that the fabric of space is knitted from the correlations between quantum states. This is not a confirmed result. It is a conjecture, a beautiful and mathematically suggestive conjecture, but if it is even approximately right, it means that the distinction between quantum mechanics and geometry, between the laws of the very small and the laws of the very large, is not a distinction between two separate domains of physics. It is a distinction between two aspects of a single structure that we do not yet know how to see whole. You are deep inside the labyrinth now. The solid floor of established physics has given way to something more uncertain, more branching, more dependent on mathematical structures whose physical interpretation is not agreed upon. And you might be tempted to conclude that this is a problem of the frontier, that the breakdown happens only at extreme scales, only in black holes, and at the Planck length and at the beginning of the universe, in regimes so remote from ordinary experience that they have no bearing on the reality you actually inhabit. You might want to believe that the rules are intact where it matters, intact at the scales of chemistry and biology and human life, intact enough for the practical purposes of understanding how the world works day to day. And in a technical sense, this is true. The Standard Model and general relativity are extraordinarily accurate descriptions of physics at the scales they have been tested. Quantum electrodynamics predicts the electron's magnetic moment to 11 decimal places. General relativity predicts the orbital decay of binary pulsars to extraordinary precision. These theories are not wrong in the way that is practically relevant to most situations, but the fact that they work so well at tested scales is not a guarantee that they are describing reality correctly at those scales. It is possible for a theory to be empirically adequate to make correct predictions while being conceptually wrong, while misidentifying what is actually happening at a deeper level. Newtonian mechanics made extraordinarily accurate predictions for 2 centuries, but its concepts, absolute space, absolute time, force acting at a distance, were not correct descriptions of reality. They were effective descriptions, useful approximations to a deeper reality in which space and time are relative, and forces are mediated by fields and ultimately by geometry. Our current theories may be in the same situation. Their predictions may be correct in their domain, but their concepts, particles, fields, space-time probability amplitudes, may be no more fundamental than the Newtonian concepts they replaced. And here is perhaps the most disorienting thing of all, the thing that makes the current crisis in physics different from previous ones. In previous transitions, from Aristotle to Newton, from Newton to Einstein and quantum mechanics, there was always a crisis in the data first. Observations that the old theory could not explain. Phenomena that demanded a new framework. The precession of Mercury's perihelion, the photoelectric effect, the ultraviolet catastrophe. Data came first, and theory followed. What is happening now is different. We have anomalies. Yes, the Hubble tension, the muon anomaly, the matter-antimatter asymmetry. But we also have a theoretical crisis that exists independently of the experimental anomalies. A crisis of foundations that is not driven by data, but by the internal incoherence of the frameworks themselves. The measurement problem in quantum mechanics is not an experimental anomaly. It is a conceptual failure, a theory that makes perfect predictions while being unable to say what those predictions mean, unable to describe what happens when a measurement occurs, unable to tell us what physical reality is like between measurements. The incompatibility of quantum mechanics and general relativity is not an experimental failure. It is a theoretical failure. Two theories that each work perfectly in their domain, but produce nonsense when applied simultaneously. These are not failures of experiment. They are failures of understanding. We have the correct equations, but we do not know what they are equations of. We have the right map, but we do not know what country it is a map of. And this is a strange and unprecedented situation, because throughout the history of physics, whenever we had the right equations, we also knew what they were saying about the world. Newton's equations described the trajectories of bodies in absolute space and time. Maxwell's equations described the oscillation of electromagnetic fields. Einstein's equations described the curvature of space-time. We knew what the equations meant. We do not know what Schrödinger's equation means, not in a fully satisfactory way, not in a way that everyone agrees on. And we have known this for 100 years and have not resolved it. That is not a sign of a field on the verge of triumph. It is a sign of a field that is, in some fundamental sense, lost. The word lost feels strong. It might feel unfair given the undeniable progress that physics has made and continues to make. Quantum computers are being built using the entanglement and superposition properties of quantum mechanics. Gravitational waves are being detected, ripples in the fabric of space-time produced by the collision of black holes and neutron stars a billion light-years away, a direct confirmation of general relativity's predictions. The James Webb Space Telescope is observing galaxies from the first billion years of the universe, revealing structures that are already challenging models of early galaxy formation in ways that will take years to fully understand. Progress is real. Discovery continues. The frontier is not dead, but progress within a framework and progress on the foundations of the framework are different things. You can navigate skillfully across a continent using a map that has the wrong coordinates, as long as you stay in the territory the map was calibrated for. The problem comes when you need to go somewhere the map has not been tested, somewhere at the edge of the known territory, somewhere the map's assumptions are stretched. That is where physics finds itself. The map works beautifully in the tested regions, but the edges are wrong, and the center, the place where the map claims to describe the deepest level of reality, may not correspond to anything at all. There are galaxies appearing in the data from the James Webb Space Telescope that should not be there. Not because galaxies at those distances are unexpected, the telescope was designed to find them, but because the galaxies that are appearing are too large, too massive, too well-formed for the time at which they are being observed. The standard model of cosmic structure formation, which describes how the tiny fluctuations in the density of the early universe grew under the influence of gravity to form the first stars and galaxy clusters, predicts a specific relationship between the age of the universe and the size of the structures that should have formed by that age. In the first several 100 million years after the Big Bang, galaxies should be small, irregular, in early stages of formation. The physics of gravitational collapse, the rate at which dark matter halos can accumulate mass and seed galaxy formation, sets a speed limit on how quickly large structures can assemble. And yet the James Webb data appears to contain galaxies from that early era that are already fully formed, already massive, already exhibiting the organized structure of mature galaxies billions of years older. These are being called impossibly massive or too big to exist galaxies, and their existence, if confirmed, suggests that either the standard model of galaxy formation is seriously wrong, or the timeline of the universe is different from what we thought, or there is some process in the early universe, perhaps related to dark matter physics, or to primordial black holes, or to physics we have not yet conceived, that can assemble large galaxies far faster than current theory allows. The data is still being analyzed. Some of the apparent anomalies may be resolved by better photometric redshift measurements or by revised mass estimates, but some will not be resolved by those technical refinements, and the galaxies that remain will be another data point in the accumulating case that the standard model of cosmology is missing something important about the early universe. The early universe, as it happens, is one of the most crowded frontiers of anomaly in all of contemporary cosmology. The theory of cosmic inflation, the idea that in the first tiny fraction of a second after the Big Bang, the universe underwent an episode of exponential expansion, expanding by an enormous factor in an incredibly short time, smoothing out the initial density variations, setting up the seeds of structure, and explaining why the cosmic microwave background looks so uniform on large scales, is one of the most widely accepted theoretical frameworks in cosmology. It was proposed by Alan Guth in 1981 and refined by André Lund and others, and it makes a specific and testable prediction. The primordial fluctuations produced by inflation should have a particular statistical character, almost but not quite scale invariant, following a specific power spectrum that has been measured in the cosmic microwave background and found to be consistent with the prediction. This is a genuine success of inflation. But inflation also makes other predictions, most notably the prediction of primordial gravitational waves, ripples in spacetime produced during the inflationary expansion that should leave a specific imprint in the polarization pattern of the cosmic microwave background. This imprint, called the B-mode polarization signal, has been searched for with increasing sensitivity for decades. It has not been found. In 2014, the BICEP-2 experiment announced a detection of the signal, generating enormous excitement in the cosmology community before the result was shown to be contaminated by polarized dust emission from our own galaxy, not a primordial signal at all. Since then, increasingly sensitive searches have found only upper limits on the primordial gravitational wave signal, pushing the predicted amplitude of inflation lower and lower into a regime that makes many specific models of inflation uncomfortable. Some models that were once considered natural and well-motivated are now ruled out by these non-detections. Others survive, but in versions that require specific fine-tuning of their parameters. And a small but growing number of cosmologists have begun to question whether inflation happened at all, whether the problems it was designed to solve are really problems in the way they were framed, whether there might be alternative explanations for the smoothness and structure of the early universe that do not require an exponential expansion driven by an unknown scalar field with unknown properties. The inflation debate is symptomatic of a broader tension in cosmology between the enormous explanatory power of the standard framework and the growing number of observations that strain it. Lambda CDM, the standard model of cosmology, rests on 4 pillars: ordinary matter, cold dark matter, dark energy described by the cosmological constant, and the inflationary paradigm. Each of these pillars is under pressure. Dark matter has not been directly detected. Dark energy has not been explained. The cosmological constant has the fine-tuning problem. Inflation has the non-detection of primordial gravitational waves and the anomalies in the large-scale structure of the cosmic microwave background. These are not independent problems. They are all part of the same structure, the same model, and the pressure on each part of the structure weakens the whole. The model still fits the data better than any alternative that has been proposed. But fitting the data better than the competition is not the same as being correct. A broken clock is right twice a day. A model with enough free parameters can fit almost any dataset. The question is not whether Lambda CDM fits the existing data. It does. The question is whether it is describing the actual physical processes that gave rise to the universe we observe, or whether it is a sophisticated mathematical summary of our observations whose apparent explanatory power disguises a fundamental incomprehension of what is actually going on. This is a question that more cosmologists are asking openly than was the case even a decade ago, and the fact that they are asking it is itself a sign of the times. To understand why this moment feels different from earlier periods of scientific uncertainty, It helps to think about the difference between a puzzle and a mystery. A puzzle has a solution. The pieces exist. The image they form when assembled is determinate. The challenge is to find the arrangement that makes them fit. Most of the great problems of 20th century physics were puzzles in this sense. The puzzle of the electron's anomalous magnetic moment was solved by quantum electrodynamics and the technique of renormalization. The puzzle of stellar nucleosynthesis, how the elements heavier than hydrogen and helium were formed, was solved by the theory of nuclear burning in stars and supernovae. The puzzle of the cosmic microwave background, the faint glow of radiation permeating the universe in all directions, was explained by the Big Bang model and the formation of neutral hydrogen at recombination. These were hard problems. They took decades of work by many brilliant people, but they were solvable within the existing framework, or within straightforward extensions of it. A mystery is different. A mystery is not a puzzle with hidden pieces. A mystery is a situation in which the framework within which the problem is being posed may itself be part of the problem, in which the question may be malformed in a way that prevents any answer within the current language from being correct. The measurement problem in quantum mechanics may be a mystery of this kind. The fine-tuning of the constants of nature may be a mystery of this kind. The origin of the universe, not the evolution from a hot, dense state which is well described by physics, but the ultimate question of why there is something rather than nothing, is almost certainly a mystery of this kind. You cannot solve a mystery by adding more pieces to the puzzle. You have to step back and ask whether you are even solving the right kind of problem. There is a physicist named Lee Smolin who has argued with characteristic directness that physics is in a period of crisis specifically because it has confused puzzles with mysteries, because it has been trying to solve problems that are actually mysteries using the tools of puzzle solving, and because the failure to make progress is not a sign of the difficulty of the puzzle, but a sign that the framework needs to be replaced, not extended. Smolin's own proposals for what should replace the framework, various ideas involving the evolution of physical laws through something analogous to natural selection across a multiverse, or approaches to quantum gravity based on relational rather than absolute properties, are not universally accepted and face their own serious challenges. But his diagnosis, shared in different forms by a number of physicists who work on foundations, is worth taking seriously. The current stagnation in fundamental physics is not an accident, not a temporary pause waiting for the right experiment, but a structural consequence of building on foundations that are incoherent, of erecting an enormous edifice of successful science on a basement that has never been properly understood. The basement being quantum mechanics with its unresolved measurement problem, the basement being general relativity with its singularities and its incompatibility with quantum theory, the basement being the standard model with its 20 or so free parameters that must be put in by hand and have no deeper explanation. The building is magnificent. The basement is a mess. And the magnificent building does not tell you anything useful about the mess in the basement. And here, in the deepest part of this exploration, you might begin to sense a shift in what kind of problem this actually is. Because the question of whether the rules of physics are fundamental, consistent, and universal is not only a question about physics. It is a question about the nature of science itself, about what it means to have a law of nature, about whether the universe has a single coherent description, or whether it is, at some level, irreducibly multiple, contextual, relational. The idea of a law of nature, the idea that there is a rule that all physical processes obey, always, everywhere, without exception, is not itself a law of nature. It is a philosophical assumption, a methodological commitment, a bet we have placed on the universe having a particular kind of structure, and like all assumptions, it can be wrong. The history of physics can be read as a series of revisions to this assumption. First, there were many laws, then they were unified into fewer, then into even fewer, and the dream is to unify them into one. But the trend toward unification, so triumphant in the 19th and 20th centuries, has stalled. The Standard Model partially unifies 3 of the 4 fundamental forces, but not gravity. The dream of a grand unified theory, which would bring together the strong nuclear force with the electroweak force, has theoretical support, but no experimental confirmation at the energies it predicts. The dream of a theory of everything, which would include gravity, has been pursued for 50 years without reaching a testable version. Maybe the trend will resume. Maybe the unification is real, and we just need a better mathematical insight to see it. But maybe the trend was a finite one, a reflection of the structure of the particular regime of physics we had access to, not a universal feature of nature that continues all the way down. Maybe the universe, at its deepest level, is not unified. Maybe it is genuinely plural, genuinely multiple, genuinely a system that does not have a single description but requires multiple, mutually irreducible frameworks to describe its different aspects. This would be, for the sensibility of physics, a form of defeat, but it might be the truth. The plurality of the universe, the idea that there is no single, final, complete description of reality, resonates uncomfortably with a set of results in mathematical logic that were established nearly a century ago and have cast a long shadow over the philosophy of mathematics and science ever since. In 1931, Kurt Gödel proved his incompleteness theorems, establishing that any sufficiently powerful formal system, any system of axioms and rules of inference capable of describing arithmetic, is either incomplete or inconsistent. Incomplete means there are true statements that cannot be proved within the system. Inconsistent means there are statements that can be both proved and disproved, which means the system is useless as a description of truth. Gödel's theorems apply to formal systems of logic and mathematics. Whether they apply directly to physical theories, which are not purely formal systems but make empirical contact with the world, is a subtle and debated question. But the shadow they cast is real. They demonstrate that even within the domain of pure mathematics, the dream of a complete, consistent, finitely axiomatizable system capable of capturing all mathematical truth is impossible. There will always be truths that cannot be proved. There will always be statements that escape the system. If mathematics itself is not completable, the question of whether physics, which uses mathematics as its language, can ever be complete, is at least open. Perhaps the rules of the universe formulated in the language of mathematics are subject to a form of Gödelian incompleteness. Perhaps there are physical facts that cannot be derived from any finite set of physical laws, true propositions about the universe that are unprovable within any complete mathematical framework. This is speculative. Gödel's theorems do not straightforwardly translate to physics, but the analogy is suggestive. In a world where even mathematics is fundamentally incomplete, the aspiration to a complete theory of physics, a theory that answers every question, leaves no unexplained fact, has no free parameters requiring values that are simply stipulated, may be more than difficult, it may be impossible in principle. And now, having traveled this far, having passed through the Hubble tension and the muon anomaly and dark matter and dark energy and quantum entanglement and the measurement problem and the incompatibility of our greatest theories and the fine-tuning of the constants and the information paradox and the firewall and the emergence of space-time and the possibility that time does not exist and the limits of mathematical completeness, you might ask what, if anything, holds together. What is the thread that runs through all of these failures, these violations, these places where the universe departs from what the rules say it should do? And the thread, if there is one, is this. Every single one of these problems arises at a boundary, at the boundary between the quantum and the classical, at the boundary between the small and the large, at the boundary between the beginning and what came before, at the boundary between the observable and the unobservable, at the boundary between information and geometry, at the boundary between what is measured and what is between measurements. These are not random failures scattered evenly across the landscape of physics. They are clustered at the interfaces, at the transitions, at the places where one regime of description ends and another begins, at the edges of every framework where it meets the territory it was not designed to map. This clustering is itself information. It suggests that the problem is not within any of the frameworks. It is with the transitions between them. It is with the assumption that the frameworks are independent, that quantum mechanics and general relativity are separate theories that each get things right in their own domain and just need to be joined at the seam. Because the seam is where everything breaks, and a join that breaks is not a join, it is a gap. The gap at the center of physics is the gap between the quantum and the gravitational, between the discrete and the continuous, between the theory that says the world is probabilistic and the theory that says the world is geometric. To close this gap, to find the theory of quantum gravity that resolves the incompatibility, that correctly describes physics at the Planck scale, that tells us what happens at the Big Bang and inside black holes, that explains what space-time is made of and how it emerges from something more fundamental, would be one of the greatest scientific achievements in human history. It would be the completion of the project that Einstein began with general relativity and that Bohr and Heisenberg and Schrödinger and Dirac began with quantum mechanics, the project of finding the deepest possible description of physical reality. But there is no guarantee that this project can be completed. There is no theorem that says a theory of quantum gravity must exist, or that if it exists it must be accessible to beings of our cognitive architecture, or that if it is accessible, It must be findable with the experimental tools we have available. These are hopes, not certainties. Compelling hopes, mathematically motivated hopes, hopes that have driven enormous amounts of extraordinary work, but hopes. And the universe has shown, repeatedly, that it does not conform to our hopes about what it should look like or how deeply it should be knowable. The scientists who work at the frontier of these questions are not defeated. That deserves to be said clearly. The people who work on the foundations of quantum mechanics, on quantum gravity, on the Hubble tension, on dark matter, on the information paradox, they are not sitting in despair at the impossibility of their task. They are engaged, excited, alive to the possibility that the next idea might be the one that cracks the problem open. The culture of theoretical physics is one of intense optimism about the power of mathematics and clever thinking to illuminate nature. And this optimism has been justified often enough that it is not irrational. The discovery of the Higgs boson, 48 years after it was theoretically predicted, is a monument to the patience and persistence of the physics community and the extraordinary precision of the Standard Model. The detection of gravitational waves, a century after Einstein predicted them, is a testament to what determined scientists with the right instruments can achieve. The mapping of the cosmic microwave background, revealing the structure of the early universe with extraordinary precision, is one of the most remarkable observational achievements in the history of science. The optimism is real, and the achievements are real. But there is a difference between optimism about solving the next puzzle and confidence about the ultimate completeness of the framework. The former is justified by history, the latter is not. And it is the conflation of these two things, the legitimate confidence in physics' ability to solve hard problems and the unjustified confidence that the framework is essentially correct and complete, that makes the current situation so philosophically interesting and so difficult to hold clearly in view. There is a particular scientist whose trajectory through these ideas illuminates the strangeness of the current moment in a way that is worth following. John Bell, the Irish physicist who proved his famous theorem in 1964, spent much of his career doing entirely conventional particle physics as a staff member at CERN, contributing to accelerator design and theoretical calculations. But in his spare time, working on what he considered a hobby, he thought about the foundations of quantum mechanics, about what the theory was actually saying about reality, about whether Einstein had been right to be troubled by entanglement, about whether the wave function collapse was a real physical process or a mathematical convenience. Bell's theorem, which he published while on sabbatical and which he expected to be a minor technical contribution, turned out to be one of the most profound results in the history of physics, a proof that the quantum world is genuinely non-local in a sense that cannot be explained by any hidden variable theory of the type Einstein imagined. Bell was deeply uncomfortable with quantum mechanics as an interpretive framework. He thought the measurement problem was a serious problem, not a solved one. He thought the Copenhagen interpretation, which dominated physics education and practice, was an evasion rather than a resolution. He thought the question of what quantum mechanics was actually saying about reality was not a question for philosophers but a question for physicists, a question that bore directly on whether the framework was right. He spent the last decades of his life writing and speaking about these foundational issues, and his work has become increasingly central to how physicists think about quantum information and quantum foundations. Bell did not live to see the full flowering of quantum information science, which has given quantum mechanics a new practical and theoretical context that makes its foundational questions more pressing, not less. But his discomfort with the foundations, his refusal to accept that the measurement problem was solved by dismissing it, his insistence that there was something real being missed, all of this looks in retrospect like the right kind of discomfort to have. The right kind of discomfort to have. That phrase is worth sitting with, not the discomfort of paranoia, not the discomfort of motivated contrarianism, not the discomfort of someone who has decided in advance that the mainstream is wrong. The discomfort of someone who has thought carefully about what the theory is actually claiming and found that the claim, when examined closely, does not hold together in the way the textbooks suggest it does. The discomfort of recognizing that the framework you are working in is not as solid as it appears, that the solid appearance comes partly from not looking too carefully at the foundations, from staying in the regions where the framework works, and away from the boundaries where it fails. The discomfort of noticing that the emperor, if not naked, is considerably less clothed than the formal presentations would suggest. This is the discomfort that characterizes serious foundational thinking in physics right now. Not doubt about the empirical results, not doubt about the predictive success of the theories, but genuine, grounded, mathematically informed doubt about whether the conceptual framework within which those results are being interpreted is correct, whether the story physics tells about what is actually going on is the right story, whether the universe we think we are describing is actually the universe that exists. And that doubt extends, in the most reflective moments, to something even deeper than the theories themselves. It extends to the nature of the scientific method as applied to foundational questions. Science works by making predictions that can be tested. The standard of testability, the Popperian criterion of falsifiability, has been the gatekeeper of scientific legitimacy for most of the modern era. A theory that makes no testable predictions is not science, it is metaphysics. But some of the most important theoretical frameworks being developed right now are, at least in their current form, not straightforwardly testable. String theory and the string landscape, eternal inflation and the multiverse, the many worlds interpretation of quantum mechanics. These frameworks make predictions, but the predictions are either at energy scales or in domains, other branches of the wave function, other universes in the landscape, that are not accessible to current or foreseeable experiments. Does that mean they are not science? Or does it mean that our criterion of testability is too narrow, that there are forms of theoretical justification, other than direct experimental confirmation, that can legitimately constitute scientific progress? These are not comfortable questions. They do not have agreed answers. And the fact that the frontier of theoretical physics has pushed into territory where the standard methodology of science cannot straightforwardly reach is itself a sign of something important, a sign that the universe, if it has the structure these theories attribute to it, may be constituted in a way that permanently exceeds our ability to observe and test its deepest levels. The universe may be extending beyond itself in ways that are, in principle, unobservable from where we stand. And if that is the case, then the question of what the rules of physics are may not be a question that physics can answer. It may be a question that physics can only point toward, only approach asymptotically, only frame in terms that reveal its own inability to resolve it. There is a sense in which everything we have explored in this journey converges on a single, terrible, fascinating possibility that the universe does not have rules in the way we have always assumed. Not that it has rules and we have not found them. Not that it has rules and the rules are too complex for us to see clearly, but that the concept of rules as we understand them, fixed, universal, eternal, mathematical, prior to matter and energy, governing all physical processes from outside the universe itself, is a concept that does not correctly describe what the universe is. That the laws of physics are not discoveries about a pre-existing logical structure that was always there waiting to be found. That they are instead patterns, patterns in data, patterns in observation, patterns that hold across the scales and regimes we have explored and may not hold at scales and regimes we have not. That the universe is not a logical machine running on a fixed program. That it is something else and something stranger, something less determinate, something that generates regularities without being governed by rules, something that produces the appearance of law without being lawful in the deepest sense. This is a radical idea. It is not accepted by most physicists, but it is not obviously wrong. And the anomalies we have catalogued, the Hubble tension, the muon anomaly, the matter-antimatter asymmetry, the dark sector, the quantum measurement problem, the incompatibility of our best theories, the fine-tuning, the variation of constants, none of these are obviously inconsistent with a universe that has locally approximate regularities without globally exact laws. Lee Smolin and Roberto Unger have argued for something along these lines in their book, The Singular Universe and the Reality of Time, a framework in which the laws of physics are not fixed and eternal, but evolve along with the universe, in which the laws themselves are subject to change over cosmic time, in which what we observe as physical law is a snapshot of a lawful pattern that was different in the early universe and will be different in the far future. In this view, the constants of nature are not constants but slowly varying quantities, drifting across cosmic time in a way that we cannot yet detect from our particular temporal vantage point. The fine-tuning problem dissolves. The constants have the values they have not, because they were chosen or set randomly, but because they evolved to those values through a cosmological process we do not yet understand. The question of why there are these laws rather than some other laws is answered. There were other laws at other times. This framework is speculative. It is not worked out in enough mathematical detail to make precise predictions that could be tested with current experiments. But it has the virtue of taking seriously the possibility that the framework itself needs to change, not just the theories within it, that the assumption of eternal and universal physical laws is an assumption worth examining, rather than a bedrock too foundational to question. And when you examine it, when you hold it up to the light and turn it slowly and look at it from all angles, it turns out to be considerably less self-evident than it first appears. Why should the laws of physics be eternal? Why should they have existed before the universe existed, as the logical structure that the universe instantiates? Laws in every other context are descriptions of patterns, summaries of regularities, abstractions from observations. The law of supply and demand is not a law in the sense of a rule that precedes markets and governs them from outside. It is a pattern that emerges from the behavior of many agents under many conditions, a regularity that holds approximately in certain regimes and breaks down in others. Why should the laws of physics be different in kind from this? Why should they be more than very precise, very stable, very widely applicable patterns? And if they are patterns rather than rules, then the question of whether they are being violated takes on a completely different character. A pattern can have exceptions. A pattern can fade. A pattern can be a local feature of a larger system that has no pattern at all. A rule cannot. And the things we call laws of physics may be patterns all the way down. The philosopher Nancy Cartwright made a version of this argument in her book, The Dappled World, published in 1999, arguing that the laws of physics are not universal truths about how the world must behave, but highly idealized descriptions that hold exactly only in carefully prepared laboratory conditions, approximately in the domains where those conditions are closely replicated, and not at all in the messy, complex, context-dependent situations that constitute most of reality. Her argument was not that physics is wrong or that the laws do not describe real patterns. It was that the ambition of fundamental physics, to find a small set of universal laws from which everything else follows, may be misguided, because the world is genuinely heterogeneous, genuinely patchy, genuinely characterized by different regimes with different effective laws that do not reduce cleanly to a single underlying structure. This view is controversial in physics, where the drive toward unification is deeply ingrained, but the empirical situation, the failure to unify quantum mechanics and gravity, the existence of separate and incompatible frameworks for different domains, the fine-tuning that suggests the constants could be otherwise, is at least consistent with a picture of physics as the science of patterns in a patchy, heterogeneous universe, rather than the science of universal laws in a unified, lawful one. And now consider what it would mean if this were true. Consider what it would mean to live in a universe that is not governed by rules but by patterns, not determined by laws but by regularities that hold in some places and times and break down in others, not ultimately knowable through a finite set of fundamental principles, but only approximately describable through a patchwork of frameworks, each of which captures a piece of the picture, without any of them capturing the whole. It would mean that the scientific project as traditionally conceived, the project of finding the laws of nature, the final theory, the theory of everything, is not a project that will ever be completed. Not because of our limitations, but because of the universe's nature. The universe simply does not have a complete description, not because it is too complex, but because it is not that kind of thing. It is not a system running on a program. It is not a machine executing instructions. It is something that generates regularities in some regimes and novelty in others, something that is partially describable and partially resistant to description, something that offers itself to scientific investigation without ever offering itself completely. This is not a comfortable picture. It is not a picture that satisfies the deepest aspirations of the physics tradition, but it may be the most honest picture available, and learning to be comfortable with it, or at least to work productively within it, may be one of the central intellectual challenges of the coming century. You have been traveling through a landscape of broken rules and violated expectations, through anomalies and paradoxes and foundational failures, through the places where the universe fails to conform to the descriptions we have built for it. And perhaps you have noticed in the course of this journey something about the nature of your own unease. The unease is not merely intellectual. It is not simply the discomfort of encountering unsolved problems. It has a different quality, something closer to the feeling of noticing that the floor you have been standing on is not as solid as it appeared, that the walls of the room are not as fixed, that the certainties you carried into the room with you have been quietly dissolving since you arrived. This is the particular quality of the crisis in foundational physics. It does not merely threaten specific theories, it threatens the framework within which theories are built. It threatens the assumption that the universe is fundamentally knowable, fundamentally lawful, fundamentally describable in the language of mathematics by creatures of finite intelligence, operating with finite instruments over finite time. That assumption is not just a scientific assumption, It is the assumption that underwrites the entire scientific enterprise, the assumption that makes the project of doing physics coherent rather than futile. And the anomalies, the violations, the places where the rules break, are not merely puzzles within that framework. They are questions addressed to the framework itself. They are the universe's way of asking whether we have understood correctly what kind of thing it is. Consider the double-slit experiment, the one that Richard Feynman called the central mystery of quantum mechanics, the one that contains, in his words, the only mystery. You fire particles, electrons, photons, atoms, even large molecules, at a barrier with two narrow slits cut into it. Behind the barrier is a detector screen. If you fire the particles without observing which slit each one goes through, they arrive at the screen in an interference pattern, the pattern of a wave that has passed through both slits simultaneously and interfered with itself. This is the behavior of a wave, not a particle. But each particle arrives at the screen as a single dot, a single localized detection event. The pattern builds up from many individual detections, each one a point, each one apparently random in its position, but collectively forming the interference pattern that only a wave can produce. The particle behaves like a wave when traveling, and like a particle when detected. And if you add a detector to observe which slit the particle goes through, if you acquire any information by any means about the path of the particle, the interference pattern disappears. The act of obtaining path information, regardless of whether it disturbs the particle physically, destroys the wave behavior. The particle goes through one slit or the other. The interference pattern is replaced by two bands. The wave-like behavior vanishes as soon as the path is known. This experiment has been conducted with extraordinary care and in many different configurations. The results are never different. The quantum system, the particle, the wave function, the probability amplitude, behaves differently depending on whether information about its path is available. The availability of information, not any physical disturbance, determines how reality behaves. The universe, at the quantum level, is sensitive to knowledge, to information, to the question of what is known and what is not, and nobody knows why. This is the place where physics and philosophy become indistinguishable, where the equations end and the questions begin that no equation has ever answered. Why does the universe care what is known? Why does the presence or absence of information about a particle's path determine whether it behaves like a wave or like a particle? What is information, at the most fundamental level, that it should have this power over physical reality? Information theory, as developed by Claude Shannon, defines information in purely mathematical terms as the reduction of uncertainty, as the answer to a question from a finite set of possible answers, as a number of bits. This is a beautiful and powerful formalism, and it has transformed the world through computing and communications and cryptography. But Shannon's information is defined relative to an observer, relative to a question, relative to a set of possibilities that someone is distinguishing between. It is inherently relational. It does not exist in the world independently of observers who are asking questions and receiving answers. And if information in the quantum sense, path information, the information that destroys interference, is information in Shannon's sense, then quantum mechanics is inherently relational too, inherently dependent on the distinction between what an observer knows and what an observer does not know, inherently characterized by a relationship between the physical world and the observers embedded in it. This is what relational quantum mechanics, developed by Carlo Rovelli, explicitly claims, that quantum states are not descriptions of absolute properties of systems, but descriptions of the relationship between one system and another, that there is no view from nowhere in quantum mechanics, that every quantum description is relative to a perspective, a context, an observer. If this is right, then the rules of quantum mechanics are not rules about how the universe behaves in itself, in the absence of observers. They are rules about how the universe presents itself to observers, embedded within it. And the rules might be different from different perspectives, might describe different realities from different vantage points, might not be universal in the way we always assumed they had to be. The relational character of quantum mechanics connects, in a way that is just beginning to be understood, to the relational character of general relativity. Einstein's great insight was that the properties of space and time are not absolute but relative, that time passes differently for observers in different gravitational fields or moving at different velocities, that spatial distances are not fixed but depend on the observer's state of motion, that there is no universal clock and no universal ruler, only local measurements whose relationship to each other is mediated by the geometry of space-time. Both of physics' greatest theories, in other words, are relational. Both deny the existence of absolute properties, Both describe not how things are in themselves, but how they are in relation to other things, to measuring devices, to observers, to reference frames. The union of quantum mechanics and general relativity into a theory of quantum gravity would presumably be even more deeply relational, a theory in which neither space nor time nor quantum state has any meaning except in relation to something else, in which the concept of an absolute observer-independent description of reality is not merely unavailable to us, but not even coherent, a theory in which the universe does not have a single story, in which every story is told from inside, in which there is no outside from which the whole can be seen. This is perhaps the most disorienting possibility of all. Not that the rules are wrong, not that they are changing, not that we have not found them yet, but that the very concept of rules as properties of the universe in itself, independent of observers, independent of perspectives, independent of the contexts from which they are measured and experienced, is a concept that does not apply. That the universe has no rules except in relation to something asking about them. That asking changes the answer. That the act of inquiry is part of what is being inquired about. This possibility dissolves every solid thing you might have been holding on to. It cannot be fixed by a better experiment or a smarter theory. It is a reconception of what physics is about, of what questions it can coherently ask, of what kind of answers it can meaningfully provide. And it is being taken seriously not by mystics or philosophers alone, but by working physicists who have been driven to it by the internal logic of the theories they are trying to reconcile. The path from special relativity to general relativity to quantum field theory to the measurement problem to quantum gravity leads, if you follow it all the way, to a place that looks nothing like the place you started from. The place you started from had a universe with fixed rules, with definite properties, with a single reality that existed whether or not anyone was looking at it. The place you arrive at has none of those things. It has relationships, perspectives, information, contexts. It has no view from nowhere. It has no absolute ground. It has only the ceaseless relational perspectival interplay of systems describing other systems, observers measuring observables, questions receiving answers that depend on who is asking and from where. This is deeply strange. It is deeply uncomfortable. It may be deeply true, and yet even in the midst of this strangeness, you still exist. The atoms of your body are following whatever rules or patterns govern atomic behavior, and they are doing so reliably enough that you are here, reading this, thinking these thoughts. The electrons in the device through which you are experiencing this are being guided by quantum mechanical principles that are consistent enough, stable enough, reproducible enough, that the technology works. The GPS system you may use to navigate your car is making corrections for relativistic time dilation, tiny corrections predicted by both special and general relativity, and the corrections work. Physics works. Even broken physics works in the domain where it has been tested. The question is not whether the rules work locally, in the regimes where they have been calibrated. The question is whether they go all the way down, whether they hold at every scale, in every context, in every corner of the cosmos, throughout all of time. And the evidence suggests, with increasing weight and from multiple independent directions, that they do not. That there are places and scales and conditions where the rules do not apply, where they give wrong answers, where they fail to predict what is observed, where they break down into inconsistency or incompleteness, and that these failures are not peripheral or trivial. They are at the very heart of the deepest questions about what the universe is and why it is the way it is. Some of the most thoughtful physicists alive today have arrived at a position that is neither the triumphalist confidence of physics as usual, nor the paralysis of total skepticism, but something harder to characterize and more honest than either. It is a position of productive uncertainty, of sustained inquiry without guaranteed resolution, of continuing to do physics while acknowledging that the foundations are not understood, while remaining genuinely open to the possibility that the next great idea will require abandoning something that currently seems indispensable. David Deutsch, the physicist who pioneered quantum computing and whose worldview is about as far from mysticism as you can get, argues that all knowledge is conjectural, that all theories are guesses, that the history of science is a history of replacing good guesses with better ones, and that this process will continue indefinitely without ever reaching a final, complete, certain truth. This is not defeatism. It is the honest epistemological position of someone who has taken seriously what science is and what it can do. Science can produce better and better descriptions of reality. It cannot produce a perfect one. It can reduce uncertainty. It cannot eliminate it. It can find rules that hold in tested domains. It cannot guarantee those rules hold everywhere. And in the current moment, it cannot even guarantee that the rules hold in the domains where they have been tested at the level of foundations, because the foundations, quantum mechanics, general relativity, are both highly successful and deeply incoherent when examined carefully. They are better guesses than what came before. They are not final answers. Nothing ever is. The James Webb Space Telescope has shown us galaxies from a time when the universe was less than 500 million years old. Galaxies that are already forming stars and building structure faster than standard models predict. It has found evidence of carbon dioxide in the atmosphere of an exoplanet, the first detection of a complex atmospheric molecule on a world beyond our solar system, a step toward understanding whether the chemistry of life is common or rare across the cosmos. It has measured the expansion rate of the universe with greater precision than any previous instrument, and it has confirmed the Hubble tension rather than resolving it, providing measurements consistent with the higher value from local methods and inconsistent with the value predicted by the early universe data. Each new discovery from Webb is a test of the standard model of cosmology, and the tests are yielding a mixed verdict. The model works in some respects and fails in others, is confirmed in some measurements and challenged in others, is revealing a universe that is partially as expected and partially full of surprises. This is the normal operation of science at the frontier. But the specific nature of some of the surprises, the two massive early galaxies, the confirmed Hubble tension, the structures at scales that should be featureless, suggests that the surprises are not random. They are patterned. They point in specific directions. They are consistent with a universe that formed structure faster than the standard model allows, that has more complexity at early times than expected, that is expanding at a rate inconsistent with the predictions of the standard cosmological model derived from first principles. If this pattern continues to sharpen, it will eventually become undeniable that something is wrong with the model in a deep way, not just in the details, but in the physics. And when that becomes undeniable, the field will face a choice between incremental revision and fundamental reconception. History suggests the incremental revisions will be tried first, exhaustively, before the fundamental reconception is accepted. That is how science works. That is how it should work. But the signs are accumulating that the incremental revisions may not be enough this time. There are physicists who believe the next revolution will come from quantum information theory, from the deep connections between quantum entanglement, quantum error correction, and the emergence of space-time that have been developing over the past decade. The AD-CFT correspondence discovered by Juan Maldacena in 1997 is a mathematical equivalence between a theory of quantum gravity in a particular kind of space and a quantum field theory without gravity living on the boundary of that space. It is the most studied and most influential theoretical result in high-energy physics of the past 30 years, and it has revealed deep connections between the geometry of space, the entanglement structure of quantum states, and the error-correcting properties of quantum codes. In particular, work by Ahmed Almiri, Shidong, and Daniel Harlow has shown that the holographic encoding of bulk spacetime in boundary quantum theory has the structure of a quantum error-correcting code, the same mathematical structure that is used in quantum computers to protect quantum information from decoherence. This is an extraordinary connection. It suggests that spacetime itself, the geometry of the bulk space in the holographic correspondence, is encoded in the entanglement structure of the boundary theory in the same way that logical quantum bits are encoded in physical ones in a quantum error-correcting code. Spacetime geometry as error correction, the fabric of reality as a redundantly encoded quantum state. This is not yet a theory of quantum gravity in our universe. AD-CFT applies specifically to a universe with a negative cosmological constant, a universe that is not like ours, which has a positive cosmological constant. Extending the holographic correspondence to our actual universe is a major open problem, but the mathematical structures being revealed are so deep, so suggestive, so unexpectedly connected to practical quantum information theory that many physicists believe they are pointing at something real about the relationship between quantum mechanics, information, and the emergence of spacetime. The emergence of spacetime. The phrase is worth pausing on. If spacetime is emergent, if it is not fundamental but arises from something more basic, then every question we have been asking about the laws of physics, the rules of the universe, the violation of those rules, needs to be reformulated. The laws of physics as we know them are laws about things happening in spacetime. They describe how fields evolve through time and space, how particles move through spacetime, how spacetime curvature affects the motion of matter. If spacetime is emergent, then these laws are emergent too. They are the laws of the emergent description. Valid in the regime where spacetime is a good approximation to the underlying structure. At the fundamental level, in the structure from which spacetime emerges, there are no spatial locations, no temporal intervals, no fields propagating through a background. There is only the underlying quantum structure, the entanglement network, the spin foam, the holographic boundary theory, whatever it turns out to be, and the laws governing that structure are completely different in character from the laws of physics as we know them. The laws of physics as we experience them, general relativity, quantum field theory, the Standard Model, are macroscopic effective laws, emergent descriptions valid at scales large compared to whatever the fundamental structure is, just as the laws of fluid mechanics are valid for water on scales large compared to atomic spacing, but break down when you try to apply them at atomic scales. The laws of space-time physics are valid at scales large compared to the Planck length, but break down at Planck scales where the underlying structure becomes relevant. If this picture is correct, then asking whether the laws of physics are being violated is like asking whether the laws of fluid mechanics are being violated near a phase transition. The answer is, not violated exactly, but superseded. The emergent description breaks down not because the rules are being broken, but because the regime of applicability of the emergent description has been exceeded, and you need the more fundamental description to understand what is happening. The laws are not wrong, they are approximate, and they are approximate in a regime whose boundaries we are only now beginning to probe. The boundaries of the approximate regime are where the universe becomes most interesting, at the Planck scale, where quantum gravity is important, at the cosmological horizon where the expansion of the universe severs our causal contact with the rest of space, at the singularities inside black holes, where general relativity predicts infinite density and zero volume, the mathematical equivalent of a theory eating itself, at the moment of the Big Bang, before which the concept of time may not apply, at the boundaries of the observable universe beyond which we have no data and no ability to gather any. These are the edges of the map, and on medieval maps the edges were marked with warnings about dragons and sea monsters, about the dangers of going beyond the known. Physics does not have dragons. It has something stranger, and in some ways more troubling. It has the silence of the unmeasured, the blank of the unobservable, the quiet of a region where the rules that govern the interior do not extend, and where no new rules have been found to replace them. Beyond the observable universe, the laws of physics may be the same as here, or they may not. If the constants of nature vary across space, then beyond the horizon, the universe operates by different rules. Physics works differently. Atoms have different properties. Time may flow at different rates. We have no way to know. We have no way ever to know. Not in any conceivable future of our civilization. The observable universe is finite, and it is all we have access to. Everything beyond it is beyond experiment, beyond observation, beyond science in the strictest sense, and everything we believe about what is beyond, about whether the universe extends infinitely, whether it is spatially flat or curved, whether the laws of physics are the same everywhere, is extrapolation, the projection of the local rules onto the unknown, the assumption that the patterns we see here are universal, even though we cannot check. This is the epistemic situation you are in. You are an observer embedded in a finite region of a universe whose extent and nature you cannot fully observe, using theories that work in the tested domains and break down at the boundaries, trying to determine the rules of a system you are inside of and cannot step outside of, asking questions whose answers may require information that is permanently beyond your reach. The situation is not unique to physics. It is the situation of any finite observer in a complex system. You cannot step outside the universe to see it from the outside. You cannot observe the universe without being part of the observation, without your instruments and your theories and your cognitive architecture shaping what you can see and how you interpret it. You are not a neutral recorder of objective facts. You are a participant in the system you are trying to describe, and the system includes you, and the description you build is always a description from inside, always partial, always perspectival, always shaped by the particular location in space and time from which it is made. This is not a counsel of despair. It is a description of the actual situation, stripped of the false objectivity that the ideal of science sometimes promotes. The ideal of science is the view from nowhere, the God's eye view, the description that would be valid for any possible observer at any possible location in the universe. But there is no view from nowhere. There is only the view from here, from now, from this particular configuration of matter and energy and information that constitutes the scientific enterprise at this particular moment in cosmic time. The view from here is magnificent. It has illuminated the structure of matter and energy from the Planck scale to the cosmological horizon. It has discovered laws that are almost universal, constants that are almost constant, rules that are almost always followed, almost. And in the almosts, in the small, persistent deviations, in the places where almost becomes clearly not, the universe is leaving traces of something that does not fit the picture, something that the picture was not built to contain, something that the rules were not written to describe. There is a particular kind of loneliness in this situation that is worth naming. The loneliness of standing at the edge of the known, looking out at the unknown, equipped with tools that have been extraordinarily successful in the known territory, and that give every sign of failing in the unknown, and not knowing whether the unknown is different in degree, more of the same, extended, more complex but fundamentally similar, or different in kind, genuinely other, genuinely beyond the reach of the current tools, genuinely requiring a revolution in thought that is not yet available. The physicists who work on quantum gravity, who have been working on it for decades without a confirmed prediction, know this loneliness. The cosmologists who watch the Hubble tension persist and deepen, who have run out of systematic errors to blame it on, who are beginning to confront the possibility that the standard model of cosmology is wrong in a way that they do not know how to fix, know this loneliness. The particle physicists who have watched the LHC produce no new physics beyond the Higgs boson, who are watching the supersymmetric particle zoo fail to emerge from the data after decades of confident prediction, who are staring at the desert and wondering whether it extends all the way to the Planck scale, know this loneliness. It is not the loneliness of isolation. It is the loneliness of having pushed the tools of your tradition to their limits and finding yourself at a boundary that the tools cannot cross, waiting for an insight that has not yet come, not knowing if it will come from a new experiment or a new theory or a new kind of thinking that does not yet exist. In 1900, Lord Kelvin gave a lecture in which he described two clouds on the horizon of physics, two small puzzles that seemed to resist explanation by the otherwise triumphant edifice of classical mechanics and thermodynamics. Those two clouds were, respectively, the failure of the Michelson-Morley experiment to detect the motion of the Earth through the luminiferous ether, and the inability of classical physics to explain the spectrum of black-body radiation. Within 15 years, those two small clouds had become storms. Special relativity and quantum mechanics dissolved them, and in doing so, demolished the edifice that Kelvin had been celebrating. The two small puzzles were not small at all. They were windows into a fundamentally different reality than the one classical physics had been describing. The anomalies of today, the Hubble tension, the muon anomaly, the dark sector, the measurement problem, the incompatibility of the two great theories, may be the Kelvin clouds of the 21st century, or they may be the first visible signs of an even deeper breakdown, a breakdown not just of specific theories but of the entire framework within which theories are built, the framework that assumes the universe is lawful, consistent, knowable, describable by mathematics, the same everywhere, the same always. This is the thing we do not know. This is the thing nobody knows. And it is perhaps the most important thing to acknowledge. Not just that specific theories are incomplete, not just that specific measurements are anomalous, but that we do not know what kind of problem we are facing. We do not know whether we need a new puzzle piece or a new kind of puzzle. We do not know whether the solution will look like string theory or loop quantum gravity or something that nobody has thought of yet, or something that is not a theory in the traditional sense at all. We do not know whether the universe is knowable all the way down or only approximately, only locally, only perspectively. We are in the position of standing in front of a locked door without knowing whether the key is somewhere in the building, whether there is a key at all, or whether the concept of a door with a key is the right way to think about what we are standing in front of. And perhaps that is where you need to remain, not on the other side of the door, not with the answer, not with the resolution, not with the new framework that makes all the anomalies coherent. That explains the Hubble tension and the muon anomaly and dark matter and dark energy and the measurement problem and the incompatibility of quantum mechanics and general relativity and the fine-tuning and the matter-antimatter asymmetry and the galaxy formation problem and the cosmic microwave background anomalies and the information paradox and the firewall and the arrow of time and the emergence of space-time and the limits of mathematical completeness, all in one sweep, all at once, all made clear and sensible and inevitable in retrospect. That resolution is not available. Maybe not yet, maybe not ever, maybe not in the form of a single resolution at all. The universe is not offering you an explanation. The universe is offering you an anomaly. It is showing you the places where the rules fail, where the predictions diverge from the observations, where the mathematical structures that describe physical reality so beautifully in one regime stop working in another. It is not telling you what to conclude from this. It is not pointing you toward the solution. It is simply continuing to be what it is, continuing to behave in ways that confirm some of your theories and violate others, continuing to present a face that is partially lawful and partially strange, partially predictable and partially resistant to prediction, partially transparent to the tools of human inquiry, and partially opaque to them. The universe is not broken. It is not failing. It is precisely exactly what it is. What is failing is the description. What is breaking is the picture. What is violating the rules is not the universe. It is the rules. Every measurement that deviates from the prediction is a message. Every anomaly is a signal. Every place where the theory breaks down is a boundary marker, a sign that says, this is where the description of reality that you have built extends to and no further. These boundary markers are not failures of the universe. They are invitations. Invitations to think differently, to question assumptions that have never been questioned, to let go of the ideas that have served so well for so long that they have become invisible, so embedded in the structure of thinking that they are no longer recognized as ideas at all but as facts, as obvious truths, as things that need no examination because their truth is self-evident. The constancy of the constants, the universality of the laws, the objectivity of measurement, the reality of space-time, the arrow of time, the determinism of evolution, the separability of systems, the independence of the observer. These are not facts. They are assumptions. Some of them may be approximately correct in some domains. Some of them may be exactly right everywhere. Some of them may be exactly wrong, the precise places where the picture most systematically misleads. We do not know which is which, and the not knowing is not a temporary condition awaiting the right experiment. It may be a permanent condition of any finite observer in an infinite or indefinite universe, a structural feature of the relationship between a mind that seeks order and a universe that is under no obligation to provide it. The question you are left with, the question that does not resolve, that does not close, that stays open like a wound that will not heal, is not whether specific theories are wrong or right, not whether the Hubble tension will be explained by new physics or a measurement error, not whether dark matter will eventually be detected or replaced by a modification of gravity, not whether string theory will make a testable prediction or be abandoned as a mathematical detour. The question is whether the universe is the kind of thing that has rules, whether the regularity we observe, the pattern, the consistency, the mathematical structure that makes science possible, is a fundamental feature of reality or a local, approximate, emergent property of the particular corner of the universe we inhabit and the particular scales at which we operate. Whether the laws of physics are eternal, necessary truths that would hold in any possible universe, or contingent, evolving regularities of this particular universe at this particular time, regularities that have exceptions and boundaries, and a history and perhaps a future in which they no longer hold. Whether the universe in the most fundamental sense is lawful at all, this question cannot be answered from inside the universe using the tools of physics as currently practiced. It may never be answerable, and the fact that it is asked at all, the fact that the anomalies and violations and failures of prediction have driven us to the point where it must be asked, is itself one of the most significant things that has happened in the intellectual history of our species. We began with the certainty that the universe follows rules. We have arrived at the question of whether there are any rules to follow. The journey from one to the other is not a story of failure. It is a story of discovery. The discovery that the universe is stranger, deeper, more uncertain, more open than we had the right to hope or the imagination to fear. And as you sit with that question, as you hold it without resolving it, without collapsing it into a comfortable answer in either direction, without deciding either that physics will eventually explain everything or that the universe is permanently unknowable, as you stay in the discomfort of genuine uncertainty about the deepest things, you are doing something that is actually quite difficult. You are resisting the consolation of false certainty in both directions. You are not reaching for the reassurance that science will eventually triumph, and the anomalies will be explained, and the rules will be found to have been intact all along. And you are not reaching for the opposite consolation, the one that says the universe is mysterious and beautiful and beyond understanding, and perhaps it is better that way. Both of those consolations are available. Both of them are wrong. The situation is more difficult than either allows. The rules appear to be breaking. Some of the breaks are anomalies that may be resolved. Some are fractures that may require a new framework. Some may be windows into a fundamentally different kind of reality. than the one we have been describing, and we do not know which is which, and we may not find out, not completely, not with certainty, perhaps not even with confidence. What we have is the anomalies themselves, precise and persistent, and the theories that cannot explain them, and the tension between a universe that is partly lawful and partly not, and the question of what that tension means, what it means about the nature of physical law, what it means about the nature of reality, what it means about the nature of the project we have been engaged in since the first human being looked at the sky and asked why it looks the way it does. That question is still open, it may always be open. And the universe, vast, ancient, indifferent, precise in some respects and inexplicable in others, continues to exist without reference to whether we understand it, continues to expand at a rate that our best theories cannot agree on, continues to be made mostly of things we cannot see, continues to produce particles that misbehave, continues to correlate entangled objects across arbitrary distances, continues to present a quantum face that is indefinite and a classical face that is definite, without explaining the transition between them, continues to have begun in a way that cannot be described and to be ending in a way that cannot be confirmed, continues to be, in every direction you look and at every scale you probe, both more like what you expected and more unlike it than anything you were prepared for. The rules were supposed to hold. They were supposed to hold at every scale, in every context, in every corner of the cosmos, at every moment from the first fraction of a second after the Big Bang to the last photon emitted by the last white dwarf in the heat death of the far future. They were supposed to be the bedrock, the invariant, the thing that does not change when everything else changes, the anchor that holds the universe together as a coherent, lawful, comprehensible system. And in the tested domains, in the familiar regimes, on the scales where human science has been calibrated, they hold. They hold beautifully, with extraordinary precision, with a mathematical elegance that has inspired generations of physicists to believe that the universe is, in some deep sense, rational, that it speaks the language of mathematics, that its structure can be comprehended by minds like ours. That belief is not entirely wrong. The universe does have mathematical structure. The rules do hold in the tested regimes. The regularities are real, but they are not universal. They are not eternal. They are not the last word. And in the places where they fail, in the gap between the early universe expansion rate and the late universe expansion rate, in the tiny but stubborn discrepancy between the predicted and measured magnetic moment of the muon, in the vast invisible bulk of the cosmos that no instrument has directly touched, in the indefinite quantum realm that becomes definite only when observed, in the singularities where geometry collapses into nonsense, in the horizon where causal contact ends and the unknown begins, in all of these places the universe is doing something that the rules do not describe, something that the rules did not anticipate, something that the rules by their own logic say should not be happening, and it is happening anyway. It has always been happening. We are only now precise enough, sensitive enough, honest enough to see it. The seeing of it changes something, not in the universe which continues without reference to whether it is understood, but in the understanding itself. In the relationship between the human mind and the cosmos, it finds itself inside. For centuries, that relationship has been characterized by a kind of confident asymmetry. We ask the questions. The universe provides the answers, and the answers fit into the framework we have built to receive them. The framework grows. It incorporates the new answers. It makes new predictions. Those predictions are tested and mostly confirmed, and the confidence grows that the framework is essentially right, that the project is converging, that the final theory is approaching, that the view from the top of the mountain will eventually be clear. But the anomalies suggest a different relationship. They suggest that the universe is not answering the questions we are asking, that the questions themselves are not well formed, not oriented toward the structure of what is actually there, that the framework is not converging but diverging, developing more internal tension with each new precise measurement, requiring more epicycles and more free parameters and more dark substances and more undetected particles with every attempt to maintain its consistency. The anomalies suggest that the universe is not a puzzle waiting to be assembled. They suggest that it is something stranger, something that generates the appearance of a puzzle without having a solution in the form of assembled pieces, something that offers the mathematician's dream of deep structure without the physicist's dream of complete comprehension, something that is precisely describable in some respects and genuinely indefinite in others, and that the boundary between the two, the boundary between what is lawful and what is not, between what is measurable and what is not, between what can be known and what cannot, is not a temporary boundary waiting to be pushed back by better science, but a permanent feature of the relationship between finite observers and an infinite or indefinite reality. And here, at the edge of what can be said with confidence, something unexpected happens to the nature of the exploration itself. The further you follow the thread of violated rules and broken predictions, the more you find yourself not in a place of scientific defeat, but in a place of genuine, open, philosophically alive uncertainty. The universe that emerges from careful examination of its anomalies is not the comfortable, clockwork universe of classical mechanics, nor the strange but ultimately deterministic universe of general relativity, nor even the probabilistic but internally consistent universe of quantum mechanics as taught in textbooks. It is something wilder and less tame than any of those. It is a universe in which the largest and smallest scales are described by incompatible frameworks, in which the most fundamental particles are point-like singularities in one theory, and vibrating strings in another, and quantum loops of space-time geometry in a third, in which space and time may be emergent rather than fundamental, woven from the entanglement of quantum states in a way that has barely begun to be understood, in which the constants that define the character of matter and energy and force may be slowly drifting, locally varying, or arbitrarily selected from an enormous landscape of possibilities, in which the observable universe is a finite bubble of causally connected space-time, floating in a larger structure, whether infinite flat space or a multiverse of branching quantum histories or a network of disconnected causal patches, that is permanently beyond direct observation and perhaps beyond any form of scientific determination, in which the rules we have found are the local, approximate, emergent regularities of this particular bubble at this particular era, regularities that have served as the foundation of the most extraordinary intellectual project in the history of our species, and that are now, at the frontier, showing the seams of their own approximateness. The seams are important. They are the most important thing. Not because they tell us that physics has failed, and it has not, but because they tell us that physics has reached a boundary that is not a temporary obstacle, but a structural feature of the situation. The boundary between what the current framework can describe and what it cannot is not a boundary that more experiments or better mathematics will simply dissolve. It marks a genuine transition, a place where the conceptual tools that have worked so well are running out of traction, where the extrapolation of the tested framework into untested regimes is producing predictions that do not match observations or mathematical structures that dissolve into nonsense. Crossing this boundary will require not just new data but new ideas, and not just new ideas but new kinds of ideas, ideas that reconceive what a physical theory is, what it is describing, what it means to explain a phenomenon, what counts as understanding. The history of science suggests that such reconceptions are possible. It has happened before, but it has never happened on demand, never been produced by a community of researchers deciding to think differently. It has always arrived unexpectedly, from an unexpected direction in the mind of someone who had been living with the problem long enough and deeply enough that they could see through the framework to something on the other side. It arrived that way for Einstein. It arrived that way for Bohr and Heisenberg and Schrödinger. It may arrive that way again, or it may not arrive at all, if the problem is not a puzzle that yields to cleverness, but a mystery that reveals the limits of the knowable. Either way, the waiting itself is significant. The fact that the reconception has not arrived despite decades of intense effort by thousands of brilliant people is a signal. It may be a signal about the difficulty of the problem. It may be a signal about the depth of the change required. It may be a signal that the problem is harder than any problem physics has faced before, not just technically but conceptually, not just mathematically but philosophically, not just as a scientific challenge, but as a challenge to the very concept of scientific understanding. You have been here at this edge for the entire length of this exploration, even when the language was talking about specific experiments and specific measurements and specific theoretical frameworks. The edge has been present throughout, growing more visible as the specific problems accumulated, more insistent as the anomalies deepened, more undeniable as the pattern of systematic deviation from the predictions of the best available theories emerged from beneath the technical details. The edge is not a conclusion. It is not a finding in the sense of a discovered fact. It is a recognition that the territory of the known has boundaries, that those boundaries are real, and that what lies beyond them is not known in any confident sense and may not be knowable in any currently available sense. This recognition is uncomfortable. It is supposed to be uncomfortable. Comfort at the foundations of physics would mean either that everything is understood, which it is not, or that nothing is expected to be understood, which would be intellectual surrender. The discomfort is the appropriate response to the actual situation, a situation of genuine, deep, structured uncertainty about the most fundamental questions that can be asked about the nature of reality. The discomfort is not a problem to be solved, it is a state to be inhabited. And inhabiting it honestly without collapsing it prematurely into false certainty in either direction is one of the most difficult and most important things that a mind confronting the universe can do. Consider the speed of light, the most famous constant in physics, 300 million meters per second in a vacuum, invariant for all observers regardless of their relative motion, the cornerstone of special relativity, the ultimate speed limit of the universe, the basis of every modern understanding of electromagnetism, of optics, of the structure of space-time. It is one of the most precisely measured quantities in all of science. It is so fundamental that its value is now used to define the meter, the standard unit of length in the international system. And yet, there are serious theoretical frameworks in which the speed of light is not a fixed constant, but varies with time. Varying speed of light theories, developed by João Magalhães and Andreas Albrecht and others, which propose that in the very early universe the speed of light was much higher than it is today. High enough to solve the horizon problem that inflation was designed to explain, to account for the uniformity of the cosmic microwave background without requiring an exponential expansion. Episode. These theories are not mainstream. They face serious theoretical difficulties and have not produced confirmed predictions, but they are not scientifically incoherent. They are mathematically consistent and empirically motivated by the same cosmological observations that motivate inflation. And the fact that they can be formulated at all, the fact that serious physicists have published serious work arguing that the speed of light might be variable, tells you something important. Even the most fundamental constants, the ones so fundamental that we use them to define our units of measurement, are not beyond questioning. There is no constant in physics whose constancy is guaranteed by anything other than the consistency of our measurements, to date within the precision and domain of those measurements, and our measurements have a precision and a domain. Beyond that precision and that domain, we do not know. We assume constancy. We have always assumed constancy. And the history of physics is a series of revelations that things we assumed were constant were not, that things we assumed were absolute were relative, that things we assumed were invariant, varied, that the ground we stood on was not ground at all, but the surface of a much deeper and much stranger territory that our assumptions had been preventing us from seeing. The territory is strange. You are standing in it right now, even as you read this, even as the solid certainties of everyday experience surround you with their comfortable density. The chair is solid, the wall is solid, the ground is solid, the laws of physics appear to be holding. Gravity is keeping you in your seat. Electromagnetism is keeping the atoms of your body from dissolving through the atoms of the chair. The strong nuclear force is keeping the nuclei of those atoms together. The weak nuclear force is governing the radioactive decays that have been occurring in the atoms of your body since before you were born. The standard model is working. General relativity is working. The rules are being followed. In this room, at this scale, in this moment, and simultaneously at the cosmological scale, the universe is expanding at two different rates depending on how you measure it, and there is no consensus explanation for the discrepancy. At the particle physics scale, the muon is rotating slightly faster in a magnetic field than the standard model says it should, and there is no identified particle or force that accounts for the difference. Across the universe, 95% of the energy content is made of things whose nature is not understood, and one of which has not been directly detected despite decades of searching. At the quantum scale, particles exist in superpositions that become definite only when measured, and what constitutes a measurement and why it collapses the superposition is not, after a century, agreed upon. At the gravitational scale, the two best theories in physics are incompatible and produce mathematical nonsense when applied simultaneously. All of this is true at the same time as the chair is solid, and gravity is working, and the standard model is making predictions that match your GPS to within meters. The local works, the global breaks. The familiar is lawful, the frontier is not. You are inside a system that is orderly in the middle and chaotic at the edges, regular at the scales you can directly perceive, and irregular at the scales far above and far below your perception. And the question of which of these, the order or the chaos, the regularity or the irregularity, the familiar lawfulness or the frontier strangeness, is more fundamental, is more characteristic of what the universe actually is a question that does not have an agreed answer. The question may not have an answer at all. That is the possibility you have been circling throughout this entire journey, approaching it from different angles, finding it waiting in different forms at the end of different lines of investigation. The possibility that the universe does not have a final description, that the deepest level of reality is not accessible from any finite number of finite measurements made by any finite number of finite observers using any finite set of conceptual tools, that the regress from theory to deeper theory to even deeper theory does not terminate in a bedrock of fundamental law, but continues indefinitely or terminates in something that is not a law in any recognizable sense. The possibility that the rules are not rules, that the order is local, that the universe is in its totality neither lawful nor lawless, but something that requires a new category, something that has no name yet because it has not yet been clearly conceived, something that the history of physics has been approaching without ever quite arriving at. And perhaps this is where the most honest summary of the current situation in fundamental physics leads, not to a conclusion, not to a resolution, not to the satisfaction of a problem solved, but to a recognition that the problem is deeper than any solution currently available can reach, that the rules we have found are real, but approximate and local, that the violations we have observed are real and persistent and not going away, and that between the rules and the violations, there is a gap that has not been closed, a space of genuine ignorance about the most fundamental questions that can be asked, a territory that is not empty, but full of the most important unanswered questions in the history of human thought, the territory full of questions, the gap between the rules and the violations, the space of genuine ignorance at the foundations of physics. These are not comfortable things to sit with, and yet sitting with them is exactly what is required. Not because sitting with discomfort is virtuous, not because ignorance is something to celebrate, not because the unknown is more beautiful than the known, though it often is, but because the alternative is worse. The alternative is the false certainty of a framework that papers over its cracks, that explains away its anomalies, that dismisses its violations as measurement errors, that maintains the illusion of completeness at the cost of honesty about what is actually known. Physics has sometimes been tempted by that alternative. The history of science contains examples of communities that maintained confident frameworks past the point where the anomalies should have prompted revolution, that protected their conceptual investments against challenging data, that confused the solidity of the mathematical edifice with the solidity of the underlying reality it described. The current moment is a moment when that temptation is present again, the temptation to say that the Hubble tension will be resolved, that the muon anomaly will turn out to be a theoretical error, that dark matter will eventually be found, that string theory will eventually make a prediction, that the measurement problem will eventually be solved within quantum mechanics as currently formulated, that patience and more data and smarter analysis will make everything cohere. Maybe it will. Maybe all of these hopes will be fulfilled, but maybe they will not. Maybe the anomalies are not resolvable within the current framework. Maybe the violations are real violations of something genuinely foundational. Maybe the rules are breaking because they were never as solid as they appeared. And the universe has been telling us this for decades, quietly and precisely, in measurement after measurement that does not quite fit the model. Maybe the universe has been patient with our framework longer than it needed to be, and is now, at the frontier of precision measurement and cosmological observation, beginning to insist on being taken seriously in its difference from what we expected. Taking the universe seriously in its difference from what we expected is perhaps the most fundamental act of scientific honesty. It requires the willingness to be surprised, not just by the specific content of new discoveries, but by the form they take, by the kind of reality they reveal, by the possibility that the reality being revealed does not fit the conceptual categories currently available. The history of physics suggests that the most important moments of discovery have been precisely this kind, moments when a measurement or an observation revealed not just an unknown fact, but an unknown kind of fact, a fact that required new concepts to describe, concepts that did not exist before the discovery and could not have been anticipated by the framework that preceded it. The discovery of quantum mechanics was this kind of event. Nobody before 1900 had the concept of a quantum state, or a wave function, or a superposition of eigenstates. These concepts were not refinements of classical concepts. They were genuinely new kinds of thing, required by the reality revealed by experiment, invented by the physicists who had to find a way to describe what the blackbody spectrum and the photoelectric effect and atomic spectroscopy were telling them. The next revolution, if it comes, may be this kind of event too. It may require concepts that do not currently exist, Not just new particles or new forces or new dimensions, but new kinds of entities, new categories of description, new ways of thinking about what it means for something to exist, to have properties, to be located in space and time, to obey rules. We do not know what those concepts will be. That is precisely why we do not yet have the theory. The concepts are the theory, and they are not yet available. Waiting for concepts that are not yet available is an unusual position. It is the position of someone who knows that the next step requires a tool that has not been invented, who can see where they need to go but cannot see a path to get there, who has done everything that can be done with the available tools and has reached a boundary that those tools cannot cross. It is an uncomfortable position. It is also, in the history of intellectual progress, a recognizable one. Galileo needed calculus to fully describe the motion of falling bodies, and calculus did not yet exist. He developed the empirical results as far as he could without it, and Newton and Leibniz provided the mathematical tool that made the full theory possible. Darwin needed genetics to explain the mechanism of natural selection, and genetics did not yet exist. He described the pattern of evolution as clearly as the evidence allowed, and Mendel and later Watson and Crick provided the mechanism. Physics today may be in a similar position, possessed of extraordinary observational data and powerful theoretical machinery, but lacking the key conceptual ingredient, the new mathematical structure, the new physical concept, the new way of thinking about the relationship between observer and observed, between information and geometry, between the quantum and the classical, that would make the next synthesis possible. This is speculative. There is no guarantee that the missing ingredient exists in the form of a single key insight. The situation may be more complex, more plural, more resistant to a single synthesis than the historical analogies suggest. But the historical analogies are the best guidance available, and they suggest that the stalemate at the foundations is not permanent, that the concepts required will eventually emerge, and that when they do, the anomalies that currently seem inexplicable will appear in retrospect to have been pointing at them all along. That is perhaps the most important framing of everything that has been explored here. The Hubble tension is not a cosmological embarrassment. It is a pointer. The muon anomaly is not a particle physics nuisance. It is a pointer. The matter-antimatter asymmetry is not an unexplained initial condition. It is a pointer. Dark matter is not a placeholder for ignorance. It is a pointer. Dark energy is not a fudge factor in the cosmological equations. It is a pointer. The measurement problem is not a philosophical puzzle for people who do not want to do real physics. It is a pointer. The incompatibility of quantum mechanics and general relativity is not a technical inconvenience. It is the most important pointer of all, the one that has been pointing most directly and most urgently at the missing conceptual ingredient for nearly a century. All of these pointers are pointing in directions that we cannot yet clearly see, toward a territory that the current framework cannot fully map, toward a reality that is more complex, more subtle, more relational, more informational, more strange than the clockwork universe that science set out to describe. The universe is trying to tell us something. The anomalies are the message. The violations of the rules are the signal. And the signal is not noise. It is not measurement error. It is not a series of coincidental glitches in a universe that is otherwise lawful and well-behaved. It is a systematic, persistent, multi-domain signal that is growing clearer with every new high-precision measurement, every new telescope observation, every new particle physics experiment, every new quantum information result. The signal is saying something. We do not yet know exactly what, but we can make out the general shape of the message, even if the specific content remains blurred. The message is this: the universe is not what you thought it was. The rules are not what you thought they were. The regularity you have observed is real, but partial, local, but not universal, approximate but not exact, emergent but not fundamental. There is something beneath the rules, or beyond them, or woven through them, that does not fit any description you currently have, and that is making itself known through the places where the descriptions fail. Pay attention to the failures. They are more important than the successes. Pay attention to the failures. The successes are the comfortable part. The successes confirm what is already believed. Deepen the confidence in the existing framework. Extend the domain of the known into regions that the framework predicted could be explored. The failures are the uncomfortable part, the part that demands something new, the part that cannot be accommodated within the existing structure without distorting the structure in ways that reveal its seams. The successes of physics in the 20th and 21st centuries have been spectacular. and they deserve all the celebration they have received. But the failures, the anomalies, the violations, the places where the rules break, deserve equal attention, and they have not always received it. They have sometimes been minimized, sometimes been explained away, sometimes been filed under, will be resolved with better data, and left to gather dust in the literature while the field moved on to questions it was better equipped to answer. The gathering of anomalies that characterizes the current moment suggests that the approach of minimizing and explaining away has reached its limit, that the anomalies are too numerous, too precisely measured, too cross-domain, too persistent to be minimized any longer, that they are demanding the kind of attention that can only come from taking them seriously as signals about the nature of reality, rather than as embarrassments to be managed. Taking them seriously means asking the hardest questions, not just what new particle or what new field or what new cosmological component might explain this specific anomaly, but what kind of universe is consistent with all of these anomalies simultaneously. What the structure of a reality must be like for these patterns of violation to make sense, not as exceptions to rules, but as features of something that does not have rules in the way we imagined. What it would mean for physics to proceed in a world where the laws are not eternal, where the constants are not constant, where the quantum and the gravitational are not separate domains, but aspects of a single incomprehensible structure that currently exceeds all our tools of description. These are the questions. They do not have answers yet. They may not have answers soon, but they are the right questions, and asking them honestly without flinching from the implications, without retreating to the comfort of frameworks that no longer fit, without pretending that the violations are temporary and the rules are safe. This is where the work needs to happen, and this is where perhaps the next understanding of what the universe is will begin. And so you are left here, in the middle of a universe that is partly lawful and partly not, partly knowable and partly beyond knowing, partly described by the most precise theories in the history of science, and partly invisible to every instrument that science has ever built. Left with the Hubble tension unresolved, the dark sector unexplained, the muon still rotating faster than it should, the wave function still collapsing in ways that no theory fully describes, the gravitational and the quantum still incompatible, the constant still possibly drifting, the cosmological principle still under pressure, the information paradox still open, the firewall still threatening, the arrow of time still unexplained, the fine-tuning still demanding, the early galaxies still too massive, the rules still breaking in too many places to be explained by coincidence alone. Left with the knowledge that the universe began in a state that physics cannot describe, is made mostly of things that physics cannot identify, operates at its extremes by principles that physics cannot reconcile, and will end in a way that physics can calculate but cannot explain. Left with the possibility that the rules were never as solid as they appeared, that the regularities are local and approximate and emergent rather than universal and exact and fundamental, that the framework within which all of this has been understood is itself one of the things that needs to be understood, one of the things that the anomalies are pointing at, one of the things that the next revolution in thought will need to transcend. Left most profoundly with the question that all of this has been circling, whether the universe has rules at all, whether the concept of a rule, as we understand it, a fixed, universal, mathematical relationship that holds without exception, everywhere, always, is a concept that applies to what the universe actually is, or whether the universe is something else, something that generates regularities without being governed by rules, something that is partially orderly and partially not in a way that no current description captures, something that has been presenting its orderly face to our instruments while concealing its deeper strangeness in the places we have not yet looked carefully enough, in the scales we have not yet probed precisely enough, in the anomalies we have not yet taken seriously enough. The question is open. It was always open. It will remain open, perhaps forever, or perhaps until someone somewhere in some unexpected moment of clarity that cannot be scheduled or predicted sees through the framework to something on the other side and finds the words, or the mathematics, or the new kind of concept that does not yet exist to describe what the universe has been trying to say all along, through its violations and its anomalies, and its persistent, precise, inexplicable refusal to follow its own rules. Until that moment, the rules keep breaking, and the universe keeps going, indifferent to the breaking, indifferent to the rules, precisely, exactly, irreducibly itself, and nothing that we have yet said about it has been quite right.